Marcus Beck. I am one of two co-hosts today for the meeting. I'm here with Dr. Chris Anastasio, right in front of me, but on the left of your screen. So we'll be sort of tag teaming today on this workshop. I'm assuming everybody can hear me, otherwise I'd be getting a lot of chat messages saying you can't hear me, but if you do have any questions, we have a small group today, so obviously feel free to chime in. We want this to be interactive, we want this to be fun, we want this to be engaging, so this is not just us talking to you guys. We want to have a conversation about these interesting topics around open science, so feel free to interrupt us at any time. But if you do have a question, like I said, you can interrupt us or you can use the chat feature, which is on the Passable website. We've been told not to use the chat through Zoom. I don't even think it's enabled, but if you have a question you want to ask just through chat, you can use the Passable website. So I'm going to share my screen to the course website. That is in the chat, as well as if you go to the actual web page on Passable, there's now a link to the course materials that we'll be going through today. Let me share my screen and show you what I'm talking about. I'll be the timekeeper. Yes, and my timekeeper will make sure I don't go over. Right, so you should be seeing the Passable website here. Down here on the bottom left, there's now a new link to the course materials. And this is going to be your resource for not just today's workshop, but for continued learning after this workshop. We've kind of developed this with the purpose that it's going to be a place online that you can go to read after this workshop. And there's not going to be any way that we're going to get through all of this material today. So we want to make sure that you're aware that what's on the website, but this is going to be kind of our foundation for what we're going to go over today. And you could always go back to this website in the future to revisit any of the topics or view anything that we went over today to sort of continue this journey on open science. So I guess I'll just, before we get started, I want to just say a little bit about myself and then let Chris say a few things. And then since we don't have a heck of a lot of people on the call today, we'll do a very quick round robin of who's on the call, where you're from, and why you care about open science, because I'm really curious about people's motivations for signing up for this workshop. So I'm Marcus Beck. I am the program scientist for the Tampa Bay Estuary program. I have been in that capacity for about 2 years now. Prior to that, I worked for 2 years at the Southern California Coastal Water Research Project in Los Angeles. And then before that, I was a postdoc at the US EPA Office of Research and Development. I got my PhD in 2013 at the University of Minnesota. So I have a background in aquatic ecology. A lot of my postdoc work revolved around water quality patterns and statistical analysis of water quality in estuaries. But the common thread along my career from grad school to now has been open science. I'm a huge use of open source tools like R. I develop a lot of software and dashboards in that capacity. In fact, my job now is to develop some of these tools to help bridge the research management divide, which is a term you'll be hearing a lot about today. So what I'm doing today with this workshop as part of my job is instilling and motivating people to learn about open science. So that's a little bit about me. Chris, I don't know if you want to say a few things about yourself.
Yeah, sure. I'm glad to be a part of the workshop today. I'm looking forward to really chatting with all of you. Some of you I recognize. My name is Dr. Chris Anastasio. I currently am the Chief Water Quality Scientist and Seagrass Mapping Program Lead for the Southwest Florida Water Management District. So a little bit of a quick background. Florida has 5 water management districts. We're not state agencies and we're not local government either. We're somewhere in the middle. So if you're from California, you have water management or water districts, kind of similar, but not. But I started my career at the Water Management District, went to LSU for a while. I know we have someone on from from Louisiana, so I'm definitely interested to hear get some feedback from them. Then I came back and joined the Water Management District again, and have been here for going about 8 years now, but really been doing work in marine ecology, both in Louisiana and Florida for probably about the last 20 years. Got my PhD at USF, College of Marine Science. Worked a lot with optical oceanography and seagrass, and I'm really happy to be here. Part of the reason why I really was excited about hosting this with Marcus is open science is something near and dear to my heart and the organization I belong to. We do things in Florida called Operate in the Sunshine, and we'll probably talk a little bit about that later, but open science is sort of at the core of what we do here. So I'm very excited to kind of delve deep into that today.
We even have our own hashtag Tampa Bay Open Sci. So feel free to tweet about that and spread the love around your region. So that's a bit about us. By the way, can everybody hear Chris when he speaks? Because we're just going off the mic on my computer. Good. Okay. All right. Well, I'm just going to go around briefly, counterclockwise on my screen. So Jonathan, say a few things about yourself and why you are interested in open science.
Yeah, Jonathan Lucas. I'm an employee of NC State University. I work in the shellfish pathology lab, and I have a master's degree from University of North Carolina, where it was more of traditional ecology, benthic oyster ecology, recruitment limitation, and some of the other just basic ecological principles there. So I use R. I don't know a whole lot about open science, but it sounds like it's a good idea, and it sounds like it might be an important way for the future. So I'm more so here to learn about it, as opposed to being someone who's currently a user and involved in the open science community.
Well, R is a gateway drug to open science. So that's how I got into it, honestly. It's a slippery slope. All right, cool. Bob, if you want to say a few things about yourself.
Sure. Bob Worth, I'm an environmental consultant in Tampa, Florida. I work for Environmental Science Associates. I was HTOTM's either last or second to last PhD student at the University of Florida, which tells you how long I've been in the industry. And I got my undergraduate degree from Middlebury College in Vermont. I mostly concentrate on coastal watershed related water quality and wetlands on the Gulf Coast. And why am I interested in open science? I missed the Tampa Bay Estuary Programs workshop, I guess, a couple of years ago now. And since then, it seems like I've been missing out on some big chunk of knowledge and, I guess, industry standards. And that's why I'm here today.
Well, I wish it was an industry standard. We're not quite there yet, but that's kind of where we're trying to work towards. So we're glad to have you on board, Bob. Laura, want to pop on and say a few things about yourself?
Hi there, can you hear me?
Yes.
Hi, I'm Laura, and I work at the Virginia Institute of Marine Science, and I'm here just to learn a little bit more about what open science is all about, and if it might be applicable to some of my work. So thanks for having me.
Fantastic, we're glad to have you. And then Amin.
Hey everyone, can you hear me?
Yes.
Awesome. My name is Amin Kiagadi. I'm a coastal flood modeler at Texas Water Development Board. Before joining that, I was doing a postdoc with Clint Dawson in UT Austin. And then I did my PhD in environmental engineering at the University of Houston. My research was mainly focused on modeling hurricanes and severe storms and their environmental impact, specifically with the spills and leaks from industrial facilities. I basically lived kind of in both worlds. One of my advisors was like all about like closed science. The other one was like completely open science. And to be honest, I see value in both in a way. But I'm here to kind of learn more because as my new role as the official project manager of Texas Integrated Flooding Framework, I need to work with open science and open resources and all of that. But I have some concerns, so I'm here to learn more. Thank you.
Yeah, and it's good to hear those concerns because we do talk about kind of the balance between open versus closed and why people might have different attitudes around open science. And there's definitely, I think, in some cases, some cautionary applications of open science that are rightfully so. And we definitely talk about some of those issues. But glad to have you here, Amin.
Thank you.
And then finally, Robert.
Hey, Robert Isdo. I'm a coastal ecologist at the Virginia Institute of Marine Science. So neat to see Laura on the call. Hey, Laura. And then, so I got started in open science, just our user, and the more I did, the better it got. And so I really came into open science primarily from a reproducibility perspective. Just I really appreciated the reproducibility options that come with R, and so I'm transitioning from student to scientist and being part of a program where data is open eventually, sort of. It's been a slow slog of trying to convince colleagues and program directors that especially as being part of a state institution with public funds, that maybe a little bit more of what we do should be a little bit more transparent and open and available. So that's where I'm hoping to pick up some more tools.
Well, great. Yeah, I've definitely given many workshops in the past focused around R. I promised myself I wouldn't teach any R during this workshop. There's going to be just a tinge, but there's definitely a lot of great tools in the R universe that can help you be more open. And one thing that I think a common theme that I've heard so far among everybody that's on this call is that it's a slow slog, as Robert, you said, it's an uphill battle. But one of the things we want you guys to take home is that, you guys are now champions of open science, so you can go forth to your own institutions and try to bring the word forward and champion for those tools in your own place of education or employment. So, because we all can sort of be advocates in open science in our own right. And one of the goals of this workshop is to sort of expose you to some of the ideas of what open science can do for you and how you can be a better advocate for it, knowing full well the pros and cons of different approaches. So that's kind of our philosophy. So I'm just going to jump right into it. I'm still sharing my screen. So this is, like I said, this is our website for the course. I've kind of talked a little bit about our philosophy of what we want you to get out of this. We only have a very small amount of time, so we had to be very careful in the topics we chose. And this is by no means an exhaustive tour of everything that's open science. That's something that would take a lot longer. So we wanted to expose you to what's possible. And like I said, sort of give you the ammunition to make a compelling case for open science when we're done with the workshop. So that's the approach. This is our agenda. We have basically 4 different modules we're going to get through. There's going to be a mix of lecture, a mix of discussion, some exercises, some what we're calling watch and learns, where we sort of go through different tools that might be worthwhile. But the 4 things we landed on were kind of like, okay, let's first start with what are the basics of open science, or sort of using the same words. We're making sure we're on the same page with what we're talking about when we say open data or reproducible or transparency, that sort of thing. And then the next 90 minutes will be tools for collaboration. So one thing that can be really improved through open science is how you work with others, not just at your own institution, but with people at other institutions. And open science gives you the tools to do that more efficiently, more transparently. And so we're going to hit on some of those tools as well. Then we're going to get into open science for impactful products, and that's sort of code for data and how you treat data as a living resource that has a lifestyle, or a lifespan rather, that you can document and make sure that the data has a life beyond its project. So we'll talk about some principles around that. And then at the end, we're going to talk about some issues around key critiques of open science and how you can sort of understand the pros and cons of different arguments, or how you can sort of dispel some myths or fears around bringing open science to folks that might not be ready to adopt these new and scary ideas. The structure of the website is we have these little icons that are meant to be kind of little markers or cues that are pointing you to what we're doing at this given point. You'll see these throughout each lesson, but basically every time you come across one, we're going to have an exercise or a discussion, or we're going to do a watch and learn, that sort of thing. So yeah, let's get started. So I'm going to be doing the first lesson. This is going to be maybe like 15 minutes or so, really just sort of covering 30,000 foot level of what is open science, what are some of the key ideas, what are some of the main terms that we use. Also wanted to mention that each one of these modules has this sort of preface of what are your goals and motivation for each module. So what I'm hoping you to sort of get out of the next 15 minutes or so is just to sort of get comfortable with key ideas and concepts for understanding open science. And why you should care about this is that I think this is your first step in your open science journey. I know that a lot of you said that you've already sort of dabbled in open science, but with this workshop starting now, this is your official path to hopefully more directed activities towards adopting more open science. So why open science? I understand that I think a lot of you already see the need for it, but I've always kind of approached it as, business as usual in science is not going to get the job done if we really want our science to have an impact beyond just let's publish a paper. So we're all taught in the sciences. We all have a research background, I think. So this little workflow might be familiar to you. This is sort of a breakdown of the scientific process, at least how I see it in terms of applied science. So identify your goals, what's your question, collecting data around that question. And if you're doing applied science, you might be developing a tool around that, like something that you're hoping managers are going to use or policymakers, decision makers are going to use. And then you're going to do your due diligence and write that up into a paper or a report. You're done. Great. You write the report, you publish it, you wash your hands of it, you go on to the next thing. Maybe if you're a little more involved, you're actually working with stakeholders or managers to help identify those goals. You're not, working in isolation. Maybe you're using external data sets from partners or other resources that aren't just, you collecting the data. You're consulting other past efforts for research to develop the tool. And, you might be feeling pretty good about yourself. You're actually thinking you're doing open science at this point because you're involving things outside of your own normal workflow. And then I think, you might be, like I said, feeling pretty good about yourself. And you say, okay, I developed this great 500-page report. It's going to answer all of their questions. You publish it. And then you wash your hands of it and you go on to the next project. But from the other side of it, from the decision maker, the manager, the politician, the people that actually do the boots on the ground work, they'll look at the report and they say, well, this doesn't answer any of my questions. It's huge. It's inaccessible. It's dense. I don't know where to look to sort of inform the decisions I need to make about a particular resource. And so there's this disconnect between what scientists think is useful and what the manager thinks is useful. And that's not just a problem for applied science, but it's something that open science can help you become much more better at, because you can make the tools accessible. You can actually make the tools more pointed towards the needs of the resource managers. You can expose the process behind it to make sure there's confidence in what goes into what could be a very costly decision. So that's kind of your motivation. As I talked about, why does this sort of conventional way of doing science break down? Well, I said earlier, there's this sort of research management divide. They talk about academics being in the ivory tower or different siloing of different communities. Well, this schematic sort of breaks down how that happens or why that happens. So I think of us on this side over here, with scientific products, creating these tools that we think are great, are going to answer all of the questions about how to address a particular resource management problem. But then you have managers or policymakers or other decision makers on this side that don't necessarily know how to traverse this gap between the scientific community and their needs. And this gap exists for a number of reasons. Obviously, there's communication barriers between how scientists talk and how managers talk, or as I was just alluding to, the results that lead to a different product aren't reproducible, in the sense that, say, if someone wanted to go back and look at what you did as a scientist, they wouldn't be able to get to the same answer because they don't know how to reproduce those results. And as a result of that, they don't have confidence in what you've produced. There's just different, information loss, atrophy of information over time because you haven't documented your data, you're not putting it online, and it just sort of gets lost in the vast network of just where data goes when it dies. So these are all concerns that open science seeks to address. And if you can overcome them, you can do open science and make sure that your research products you're creating can actually have their intended impact and they can reach the audience that needs them to make decisions. I often like to showcase this graphic. I think it's a great tool to demonstrate how, if you're not doing open science, information loss can progress over time. And so this is from a paper that came out in the late 90s, believe it or not, but sort of shows how, like I said, you write the paper as a scientist and you sort of move on to other things. In the absence of tools or workflows to make your research open, not just the product, but how you made that product in the first place, you can get into this sort of situation where just through entropy or just not documenting your data sets, you lose very intimate details about a product as you move on to something else, because your mind is elsewhere, or even worse, you lose a laptop, or the lab burns down in a fire, or somebody goes on to a different job, or they get hit by a bus, whatever. Basically, in the absence of you want your science to be able to be interpretable and reproducible by others. And if you're not covering your bases, this is sort of how information does get lost over time. So again, this is a problem that open science seeks to solve. And there's going to be a few memes in here, I apologize, but I like this one. People laugh about this. They say that, oh, we don't know how these results were obtained because the postdoc that developed it left and opened a bakery. Haha, that's a problem.
I've got a real world story about that. When I joined lab at LSU, it essentially was a postdoc, and this was a while. This would have been around 2000, so we're talking a couple decades. But for those of you who like using Apple iOS, at that time, Apple and Microsoft did not talk to one another, and I stepped into a situation like this as well. And that's why I love this meme, because I remember walking into this cube of my predecessor, and everything was in Apple Mac format, and nobody knew what the file structure looked like. And worse yet, I really didn't know how to work my way through it. So it took me probably 6 months just to figure out what was even there, and then another 6 months to figure out what to do with it, at which time I decided I should probably go elsewhere. So
yeah,
it's a very tough transition.
Yeah, I'm sure everybody on this call can give an example of this happening. I can think of at least half a dozen instances in my short career to date where it's like, how did this data come about? Who created it? We don't know. The person left. So what they say is, you want your buzz factor to be high. So in other words, if you were to be hit by a bus, your work should be able to be picked up by anybody without knowing, what's inside of your head. So you, as a responsible open science practitioner, should keep your buzz factor high. You should make sure that your data, your processes are out there and documented in a way that anybody could pick them up if you were to be hit by a bus. Kind of morbid, but that's one way to think about it. So that's kind of why open science. Now I'm going to just talk about some basic ideas of what is open science, so we can make sure that the terminology we're using and our understanding about it at this 30,000 foot level are on par before we move forward with some of the other modules. So this is a nice graphic that I think, is an expansion on that initial graphic I showed. So here's the scientific process or the scientific workflow down here, but you notice that now the lines are dashed, they're open, it's no longer closed, but there's all these other great things going on here that you can, these activities you can pursue as part of your open science toolbox to make sure that you're actually producing things that others can get their hands on and understand how they're created, or you're actually producing tools that aren't just a dense, 500-page report. They're actually sort of decision support tools that can go that extra mile to actually, empower decision makers to accept the science and make more informed decisions. So again, just sort of illustrating how that general scientific process can be expanded using open science tools. I often struggle with finding a definition for open science because a lot of people have their own definitions, but I've been using this one right here for a couple of years. This comes from a couple of different sources linked up here, but basically, I think this is a nice summary that says open science is the practice of science in such a way that others can collaborate and contribute, where research data, lab notes, and other research processes are freely available under terms that enable reuse, redistribution, and reproduction of the research and its underlying data and methods. So a big mouthful there, a lot of ideas, but I think this is a comprehensive definition where if you look at the things I've highlighted, hit on some of the main themes of what open science is. So collaboration, people can contribute in sort of same platform. Data is freely available. It's, reusable, reproducible, all that great stuff. If we're going to sort of break it down even further, this is another way I think about it. So this is actually something that I thematically developed around what I think open science is. And I kind of put it in these three different boxes, right? So you can think about open science as open data. So a lot of times people say open science, they talk about making data more open, and that's certainly one aspect of it. We're talking about making data publicly available so anybody can get their hands on it. We're talking about the workflows going into creating the data should be reusable and transparent. And we often talk about data provenance, which is a fancy word for sort of what's the history of a data product, what's its life cycle, how is it created, where is it going, documenting all of those things. And we often talk about metadata as a way to do that. We talk about open process, that's the second box. And so this is kind of talking about data. You can make data through an open process, but it also talks about more general workflows, how you created an analysis, how you created a paper. Different collaborative tools to do that. So when I think about open process in my own workflow, I think about, say, like using R or R Markdown files to sort of use an open source environment to create something using Word, all integrated, and I can put them online. And then open products. So, you might think about a paper in conventional scientific literature. Is that an open product? Some would say yes. A lot of people would say no. Oftentimes it's behind a paywall. So, that's just sort of one example. There's definitely other open products. In my mind, I think about dashboards as a way to do that. So I often, I produce a lot of R Shiny apps as decision support tools. That's one product you can make very open, sort of guiding people towards their own answer, how you create the dashboard to sort of define, details of a particular product. So those are kind of three conceptual boxes, again, that I think about open science in that context. So hopefully that was helpful, sort of understanding a general definition of open science. But I also want to talk about the FAIR principles. You often see this as brought up a lot when people talk about open science. So when people say, oh, I do open science, I follow the FAIR principles. Like I said, they kind of go in the same sentence at the same time. So these are kind of guidelines or benchmark principles for thinking about how you should do your work. They're not really rigorously defined principles, but they're sort of ways. I always view them as kind of concepts in the back of your mind when you're doing work. You got to remind yourself, oh, am I being fair? Am I doing everything that I should try to be doing to making sure that I'm producing something that's findable? So anybody that, is searching for what you're doing should be able to find it. And there's different tools online that could help that be achieved? Or am I doing something that's accessible? So I'm putting something online and people can actually access it in a way that it's not behind a paywall, or it's otherwise they can get their hands on it. Interoperable. So in other words, it's not like using some proprietary format that's specific to, licensed software. There's different open source standards that people can use to make sure that no matter what platform you're on, anybody can use it. And then reusable, that's the last one. So in other words, is something reproducible, or can it be recycled in different contexts? And that goes a long way towards what we talk about when we say open science can help science as a whole progress beyond just, say, here's one data set for one project. Ultimately, that could be used for another project. And if it's not reusable, it's not using standards accepted by the community, that can really stifle creativity and really limit the scope of your particular research. So keep those in mind. Like I said, those are kind of just broad principles, but it's often useful to remind yourself to think about them when you're doing your own work, that you're, following the FAIR principles. And a lot of the tools we'll talk about today in some of the later modules will hit on different ways you can, say, be findable or be accessible. So again, we're speaking broadly about these principles, but we're going to do a deeper dive in some of these things later on. And then the last thing I want to talk about before I hand it off to Chris is this idea about schools of thought around open science. And I actually came across this paper a couple months ago, and I've been including it in open science lectures I've given because I like it, because before I saw this, I was realizing that when I think about open science, I'm thinking about it in a particular context. Other people might think about open science in a totally different context. And after reading this paper, and in particular seeing this graph, I realized that when I talk about open science, I often think about it from the infrastructure school. Openly available platforms, tools and services for scientists. So like the R universe of tools that are available, that's kind of like the infrastructure platform. Putting things online in open repositories, that's sort of that same idea. But there's other ways to think about it. There's like the pragmatic school of, making sure the process of knowledge creation is more efficient and goal-oriented. Or there's the public school. So when people talk about citizen science as a way to make science more open, that's often considered the public school of open science. So I don't want to go through like all of these, but just make you realize that oftentimes people talk about open science differently, and just to realize that, say, oh yeah, if you're talking to somebody, they might be conceptualizing it a totally different way than you are, and just be respectful and mindful of that when you're trying to advocate or sort of understand somebody's motivation for what they mean when they say being open. So yeah, I think that's about all the time we have for the first module, but I want to just stop there for a second. Again, a lot of information, 30,000-foot view of what open science is. But are there any questions about any of these concepts before we move on?
So we had a question about if he could use some of the figures from the reports.
From this workshop?
Amin, is that what your question was about like the material that you're seeing?
Yes.
This is, okay, so this is actually an important question that leads to another discussion. So a lot of open science products often come with a license. And if you go to the bottom here, I have this license down here. This is on the main page of the website. This is a very common license that's used in the public domain. Particularly, a lot of open science products use this. This basically says you can do whatever you want with the material on this website. So yes, short answer is you can reuse any of this. I've credited some of the graphics because they come from papers that might be under copyright, just to cover the bases there. But when you're working in open science, the understanding is that there's kind of guidelines of how people can reuse the material, and that often comes in the form of licenses. And I have to admit, the world of licensing is something that I'm not super well versed in, but I do know that there's different sort of grades and levels, and a lot of the open science products typically use very liberal licenses in terms of what people can do with the information. This one that I use here is basically like, you can use whatever you want. You don't even have to credit me, but there might be other ones that say you can use whatever you want so long as you credit the creators of the content. But I'm very sort of socialist when it comes to open science, and I like to be non-restrictive and how people use these materials. I mean, the goal is to sort of make sure that you guys can get as much as you can out of this information. And if you get that through reusing this information, then my job has been done. So, yeah, does that answer your question, Amin?
Yes, thank you very much.
Okay. Any other questions before we hand it off to Chris?
All right.
Cool. Well, we're going to do.
I'm just going to sit next to you because
Okay.
there's some things that we're going to do a little bit of a watch and learn here. So if you want to just stay right where you're at, I'm going to come over
Sure.
to this side of the room. And we're going to roll right into lesson number 2. So we've got about 90 minutes set aside for this one, and we're going to get into some meaty stuff here in terms of version control and really look at some of the tools that are available. We're not advocating one tool over another, but we are going to kind of delve into one or two and just show you some examples of how we can use these tools for collaboration. So the first thing we're going to do is we're kind of going to talk a little bit about what is collaboration. Like, what are some of the methods that we use? That's all of us in our various jobs to collaborate, and what are some of the pros and cons. And then we're going to kind of hopefully leave you guys with some ideas on how you might be able to build your toolbox and as you journey towards open science. So the first thing we're going to do is just kind of talk about some of the essential elements of collaboration. And the first one that we're really going to talk about is workflow management. So collaboration, at least in my mind, takes a lot of different meanings. So it could be collaborating with colleagues, collaborating across disciplines. In the case of this workshop, I'm collaborating with Marcus, two different organizations working together. But what we're going to really talk about here is how you manage your workflow. So we're going to talk a little bit too about version control, but so when we're talking about workflow management, we're really talking about it from the perspective of how does your day-to-day work flow? How do you organize your work each day? And this is, again, one of my favorite of many of the cartoons that we have in this lesson plan, which is basically how do you get from here to there? And it can, and again, we're talking about data here. So workflow management in the example that you see here on the screen is largely a function of, how you organize your documents, how you organize your data. The example I gave at LSU is a good example. This is, basically what I stepped into, as Marcus has at least once or twice, and I'm sure all of you have as well. So, yeah, we're kind of talking about data management here, but it can be scaled up to, a collaborative work environment as well. And one of the things that we wanted to kind of take a little bit of time to introduce here is this concept of Kanban. So how many of you all are familiar with this type of workflow management? Has anybody heard of it? You can just unmute yourself and say yay or nay.
Nay.
No.
No? Okay. Yeah, that
I
is
figured a lot of people would know about it, but
I've heard about it in the context of project management. Is it related to Six Sigma?
I don't know.
Yeah, we kind of talked a little bit about that. I think there are some elements that are similar to what Six Sigma does. But again, this was created really as a way to develop software. So it's a software development tool that can be used in a larger context.
Yeah, you and I were talking about.
Yeah.
Chris and I were talking about that a couple weeks ago when we were planning for this workshop, and
I think we decided that the only similarity is that Six Sigma uses post-it notes.
Yeah, and we talked a little bit about, I don't know if y'all are familiar with the SWOT principle: strength, weakness, opportunity, and threats. It's not really like that, except like Marcus said, I mean, it could involve the use of sticky notes, which you see in the example that you're seeing on the screen. But it's a simple idea, and it's basically a way to task orient your workflow. I think the best analogy, if you're not familiar with Kanban, would be the Gantt chart. So if y'all are familiar with how a Gantt chart works, it's kind of the same idea, except you're kind of using these, what they're called cards. So that's what this graphic is showing you. And again, this graphic on the screen is an example from software development, which is kind of where it came from. But what it does is it allows you to provide kind of a big picture of your progress, and then breaks it down into small chunks, like little bite-sized pieces. So I guess in many respects, it is similar to a Gantt chart in that.
Yeah, it's very close to a Gantt chart. And one of the points that I think are worth making here is that it can be a literal physical board in your office, which is one application, but what it means for open science is, well, if you're doing it in your office on a board, that's not necessarily open because it's only in your office, but
Unless the door's open.
unless, yeah, I suppose.
Or you're in a cube.
Yeah, but a lot of the platforms that we're going to talk about in a bit use this in a digital format to help you organize your workflows. And it's a way for you to conceptualize what needs to be done for a project into these discrete tasks, but other people can be a part of that process. And so I'll just leave it at there, but we'll get to what that means in an open science platform.
So does anybody have any questions about Kanban? It's Japanese, right? What is it? I forget what
I think it is Japanese, yeah.
It's a Japanese word. Anyway, there's a link in this outline that will take you to, if you want to learn more about that specific approach to workflow management. All right, so we're on to watch and learn. We want to do that before we got into version control?
I think there's another watch and learn at the end of version control.
Okay, I think we should go through version control.
Okay, yeah.
Yeah, because this is really important for those of you who, I'm assuming it's everybody, manage data. You know that version control is very important, as well as if you, working on a manuscript, if you're working on a report, having that version control is really important. And again, just like the text says, I'm sure many of you have fallen into this trap where, it just gets so unruly that you can't really remember who did what. I run into that every day in my job. I review a lot of manuscripts, I review a lot of reports, and I don't typically do that alone. So there's usually folks both within the organization and outside of the organization that are working oftentimes on the same document. So it's important that you have really good version control, or you could fall into this trap quite easily, which I know I have more often than I care to remember. So what is version control? I mean, it's basically a way that you can track the history of a project. Again, a lot of this stuff comes from the world of software development. And so when you're developing software, when you're writing R code, when you're writing, HTML script, and you're doing it in a collaborative form, which is more often than not how these things are done, it's really important that you know what folks have done. Now, again, you can apply these tools to your own work if you're working alone as well. It doesn't have to be in a truly collaborative environment. It could be just yourself, because I know many times I've made changes to a document, I've made changes to a data set, and I go back, a week later and I have no idea what I did. So it works at the personal level as well as in a group setting as well. But what version control does in this context is it allows you to formalize that documentation. So you have a paper trail, if to use kind of a dated term, in order to be able to track the changes as you're developing the product, whatever that product may be. It also helps because it makes it permanent. So going back to what Marcus said earlier about thinking about the next generation, thinking about the future you in the world that are going to look back on the work that we did today. These version controls are permanent. They go along with the data. They go along with the code. And again, it provides that system of collaboration across platforms, which is really important because as we're going to talk about, I think throughout this workshop, what is in vogue today will probably not be tomorrow. So we're all excited about using R. I'm probably 100% certain if you come back 10 years into the future, we will not be using R. It will be some iteration of that, and 10 years is very generous. How things change so rapidly in the technological world. It may be next year that we're on to something else, a different letter. So that's why version control is very important. And what we're going to do is kind of give you some examples. So Git, how many of you? Okay, again, if you are familiar, you can unmute yourself and tell us. Are you all familiar with Git and how Git works? And what Git is, as opposed to GitHub? There's some subtle differences there, or maybe not so subtle, but does anybody use Git or GitHub or is familiar with it?
I use GitHub.
GitHub, yes.
Yes to both.
Very good, cool. Yeah, so.
Can I ask how you use it?
Yeah, good
Like, do
question.
you use it just for your own work or do you use it for working with others or both?
Passively.
All right.
I did some collaboration in it, but not that much. We did some version control in it and editing and all of that, but I wouldn't say that I'm expert on it.
Yeah,
Okay.
primarily my own work.
Well, just because you are using it only for your own work, I wouldn't consider that a negative thing. In fact, I would consider that as maybe one of the more important applications of Git and GitHub, because as Chris was alluding to, it's definitely something that can facilitate collaboration with others. The most important collaborator you'll ever work with is your future self. And I totally stole that term from Julie Stewart-Lowndes, who's a huge advocate for open science, actually an inspiration of mine. She runs a program called OpenScapes. It's all about teaching and training people to become champions of open science in their own right. And she's got all these great, terms for how these things can be useful and used. And your future self is definitely somebody that's very important, maybe more so than your collaborators, because think about 6 months from now when you're like, where's that file I was working on, or what did I do to it last? I mean, I'm sure all of us have been in that situation. You got to dig through your hard drive, you got to go to that, that deep cavern of information on that graphic that we showed. And you can avoid all that nonsense by using version control. You've got that record there, you see exactly what's been done to a project. And I use it for 90% of the stuff that I work on. And 90% of the stuff that I work on is stuff that only I touch. And the other 10% is stuff I work with collaboratively. And, that's just how it goes sometimes. And it works equally well in both, like I said, collaborative or at the individual level.
I'll give you a real world example, and Bob, you'll appreciate this because Bob and I are actually collaborating on a project. Here at the Water Management District on the west coast of Florida, we have things called SWIM plans, surface water improvement and management plans. They're supposed to get updated periodically, in theory, every 5 years. But some of our plans are quite old. Some are more than 20 years old. So going back now, we're rewriting or we're updating the Tampa Bay SWIM plan. And it was last published in the early 2000s. So there's a lot of stuff that we have to go back and look at and try and recreate that. The people that were working on those projects are long gone now. So it definitely is something that we're looking ahead to, and being able to create this version control at all levels of what we do, from plan development to data collection and analysis, is going to help the future us when we go back and update the plan again in another 5 or 6 years. All right, so we're going to kind of roll into a watch and learn. So we're going to talk a little bit more about Git, GitHub, and RStudio. So it sounded like there were quite a few people that are working with R or kind of familiar with how our studio works. We use it here. Unfortunately, I'm not able to spend as much time as I'd like to learn all of the tools that are available. It's a very powerful software package. And of course, it, I think, exemplifies open science. So what we're going to do now is we're going to go ahead and do a little watch and learn. So Marcus, do you want to go ahead and drive the bus?
So we had 2 watch and learns, kind of getting at 2 topics, separate topics, objectives of showing them to you, but I think we'll just sort of roll them all into one massive watch and learn. So I want to show you how to kind of set up a version control project in RStudio, just to sort of walk you through the steps, not necessarily to show you exactly all the pieces of version control, but just to demonstrate kind of how simple it is if you've never done that. Just to sort of compartmentalize in your own head. Well, obviously, I think most of us know what RStudio is, but how does it interface with Git? And then how does it interface with GitHub? And just sort of how do you set that up and to develop a more collaborative environment? And then I also want to show you a little bit about workflow management on GitHub, because we introduced the concept of the Kanban workboard, and GitHub is a platform that has the ability for project management through that same style of Kanban workflow. And so that is a very powerful tool that I think is underutilized for collaborating with others, because it opens the door for other people to work on a version control project that might not, say, use RStudio or understand the intricacies of Git. Like, you can have a collaborator that just knows how to use a web browser, but still be engaged in a version control project. And that is, I think, tremendously powerful for collaboration, by just getting everybody involved and working on the same platform. And again, just to distinguish between Git and GitHub, the workboard is a feature on GitHub that they've made available that's just the next step beyond version control. That's not a strict part of version control, but it's just a nice little add-on feature that really exemplifies the value of GitHub as a platform for hosting and working with version control projects in an online environment. So I will, I'll show you my workflow for setting that up. So I'm going to go to my GitHub page. So this is actually what you're looking at now is the repository for all of the material for our website. In the spirit of open science, it's all there. The source content is there. But if I were me and I'm not giving a workshop right now and I wanted to start my own version control project, I would go to my GitHub webpage here. So github.com, go to my repositories, and then create a new repository. So I'm just going to name it test repository. Since this is just the example, I'll say materials for a workshop. Just make that bigger so you guys can see it. Make it publicly available. So the other option is you can make it privately available if you want to do this without anybody seeing it. I don't want to tell you not to do that, but it kind of goes against the spirit of open science. There's obviously very real scenarios where you might want to have a private repository. I'm not sort of dismissing that, but just to emphasize, if you really want to make the value of this in an open environment, you should probably be working publicly. So I'll do that. I'll create the repository, and then you end up at this page. So at this point, I need to basically point RStudio to this URL so I can have my local version on my computer, RStudio, talking to the repository that's now online. So I've got RStudio already fired up here. Move it over to the screen that you can see. So I'm going to copy so I can use it in the setup process. This is a RStudio project I've already got open. This is an existing one. Just hypothetically, I was working on this before the workshop, but if I wanted to make a new repository, I would go new project. And then I would pick the version control option. And just FYI, if you already have RStudio installed, you also need to install Git from the Git website to use this feature, but it's very simple. Just Google Git, download it, and then RStudio will recognize it on your computer, and you should be able to set this up through version control. But pick version control, pick Git, and then I'm going to paste in that URL from GitHub that I just copied. I'm going to call it, let's see, I think that actually gets pre-populated once I create the project, but I'm just going to basically put this project on my desktop. I create the project. Okay, so now basically I've just set up a new RStudio project. Hopefully if you're using RStudio, you're already familiar with projects. I strongly encourage you to use projects as a more sort of modular way to keep all of your data and files in one directory. But now it's integrated onto the GitHub repository that I've set up. So if I go back to GitHub, I'm still at this page. So if I were to refresh it, I would still see this kind of setup portion telling me how to link the two things. But I'd have to basically now do this little dance that then documents the changes in the project and pushes them up to the repository. So then it's available on that sort of cloud platform on GitHub. So these are two files that are created when I set up the repository or the project in RStudio. This is an Proj file. So this is basically a file that comes with every RStudio project. It's sort of instructions to RStudio that tell it that you're now in a project directory. This file is kind of a little text file that says you can sort of add things to this file that you don't want to put under version control. There's various reasons for doing that, but for the most part, you probably will just ignore that file. But this is kind of a blank project now with nothing in it. But I want to make sure that this is kind of synced up to the GitHub repository that I've set up. So what I'll do is I'll do this thing. I'll basically stage these files, which means I'm going to sort of stage them for being pushed up to GitHub. As you're working through a different project with different tasks or things you're trying to accomplish, there might be times you want to stage one file and not another. I usually stage everything at once, but you know, there's different sort of schools of thought around how to approach that. But for now, I'm just going to stage both these files, meaning they're going to be ready to go up to GitHub. And I can do this thing called a commit. And this is a critical part of version control. The commit is kind of like saving the state of the project at where it's at now, but it's not quite the same as like saving a file. It's kind of just a snapshot of the changes that have been made to this project. And it comes with a narrative description or a commit message that is a nice sort of thing that describes what's done. So if you're sort of looking through the history of a project under version control, you quickly read these messages to see what the changes have been throughout the history of a project.
Is there a rule of thumb when you would do that? So like, is this akin to hitting the save button when you're working on a document?
No, saving is kind of like, oh, I've done some stuff. Let me just make sure, you know, if the computer crashes, I can retrieve it. Committing a file is kind of more like, this is a state in the project that makes sense to me, that I've done some fixes or changes that I want to document. So like if you were like using the ideas from software development, you know, say there's a bug that somebody encountered in software. Ideally, someone would start working on that bug or a fix for that bug. There'd be a set of changes to maybe 1 or 2 or 3 files, depending how complicated the software is. And then once those changes are done, that's sort of like an addition to the project that should be documented. Because if, say, someone wants to understand what's been done to this project over time, like say something worked now, it didn't work before, whatever, this commit is a nice snapshot of the changes that were made to address this particular bug. So it's kind of like, it's more tangible than just saving a file, if that makes sense.
Yeah. And it's really up to you as the user to determine how substantial of a change was made to document it.
Exactly. So again, it's just all about developing that narrative history of what has happened to a file over time, or many files in this case, if you're working in a project, and you can document all that through Git and GitHub. So oftentimes, this is the first commit in a project. So there's not really anything to say about what's been done. So I'll just say in my commit message, first commit. You can call it anything else, say, this is my first commit, or whatever, this is my first commit. So I hit click, and now a lot of magic happened there, but basically now it's just a snapshot of this is a change that's been made. This is now documented through version control. And I'll show you actually what that documentation looks like in another project, but just sort of going through the exercise of this is a commit that's been made, how you do it. So then you close that, and then you've made the commit on your own computer, but now you want to push those commits up to GitHub so that anybody can see them if you're working with other people, or say you go to a different computer that's in a different place, you can pull down those changes to that computer to work across different platforms. So I'll push that up to GitHub, does this little dance, saves it, and then it pushes it up to GitHub. So if I go back to the page and I refresh it, now it's sort of started this the files I just changed on my local computer, they're there. If I go to the commit log, say, oh, this is my first commit, it's in that log. So again, I'm sort of showing you this little dance to sort of demonstrate that if you're already using RStudio, it's very simple to just kind of make that next leap and start using RStudio projects integrated with GitHub and this sort of more formalized framework. And this is a pretty trivial example that doesn't really show you the value of documenting these changes, but I'll show you an example of a more involved project. So this is our group web page that we use at the Estuary program. And there's 52 repositories on here. And each one of these repositories does something different, but I'll show you the Tbep tools repository. This is actually an R package we've developed to help us pull in data from our partners and do some synthesis of that data and create some actual reporting products from that information. And so we do this routinely, and we wanted to make sure that we had software that actually put those routines into a more formalized environment as opposed to just doing that by hand in an Excel sheet. But anyway, this is a project that has 578 commits. And so rather than like on my own computer, say, saving these files each time without knowing what the heck happened to each file, I can look at this long sort of history of all of the changes that have gone into this project of what the changes were over time. And so if I were to pick any one of these, so this is like the last change that was made to the software going all the way back in time. So it's literally a log of the changes. And so this one, like, I don't remember what the heck I was doing on August 1st, 2021, but if I look at this little note reminds me, oh, I was reprocessing the benthic data that fueled, one of the functions or the reporting functions for benthic assessment. And so I could click on that and kind of see the changes. Actually, that's a terrible example because this is a binary file and they're difficult to track. But let me find a good one. Fixing title creek examples. Yeah, so I was just changing some of the documentation in this file to be up to par with some updates for the data sets. And so what this sort of screen shows you is the changes that happened at that point in time. And so this is the old version of the file, and this is the new version of the file. And I can very quickly see that, oh, I changed this number to this number. And that might seem stupid, but there might be a point in time where like your boss calls you or they're like, this used to work, but it doesn't work anymore. It doesn't work now. And you want to be able to figure out or diagnose what the changes were that maybe had caused this. And in a worst case scenario, even sort of revert back to a version of this that was working.
This is also really important as technology advances to be able to go back and look at the sequence of events that where you made the changes and why you made the changes. I think back to the JavaScript fiasco that you know, a lot of media never really saved their versions and the nuts and bolts of how their, you know, their news stories were put together. And so a lot of that stuff now is being lost because they don't have the ability to go back and look at it. So this provides you with a look back, but it also can be very helpful for looking into the future with follow-on versions of these tools. Now, I had a question. So does this auto-populate? So when you commit, it's going to give you a snapshot of, because I notice it's giving you the lines just before and the lines just after the change that was made.
Yeah, this is something that GitHub does for you. So the software Git itself will literally, when you make that commit, it looks at all of the files that have been changed and where what was in the old version differs from what's in the new version. And it actually will identify where those changes have been made. And what GitHub does then is that it takes that differencing and actually puts it in this nice sort of GUI graphical user interface style, so you can actually look through them one at a time. You can literally look through these on Git on your computer, but it's not quite as simple as if you were doing it on GitHub. So this is a really more accessible way to start using Git in a nice, maybe more familiar interface. Yeah, so this is, again, 90% of what's been going on in this repository is stuff that I've done to this software. And so this is more of a record for me to know what the changes have been. It's kind of like an insurance policy. Like if someone's using this software, you know, if they have an issue with it, I can understand all of the changes that have happened to this since it's been first developed. If, you know, I ever need to go back and understand if I did something that broke it, or you know, there's a different version that was working that no longer does. So,
and the what looks like, what are these on the right side of the screen? You've got like
yeah, so these on the right side of the screen, what you're looking at here is this is kind of this, it's a hash number, which is a set of numbers and letters that are literally an identifier for that particular commit. If you're into cryptocurrency at all, it's sort of the same principle, where each individual transaction has a particular ID, and it's this very long sort of random string of numbers and letters that then can be tracked by its unique ID. And so the commit is the same idea. It's like a stamp on the project at any point in time. And so that's what that number shows. What's kind of cool about this is this little tab right here lets you kind of visit the repository at that point in history. So if I'm looking at it now, just from right now, this is the state of where it is from the last change I made. But if I wanted to understand where it was at, say 200 commits ago, I could go back in history and say, click this and see, oh, this is kind of like where I just clicked the little two arrows. And now this is where that repository was at that point in time. So I often do this for troubleshooting and say, oh, I knew I did something to this file. What was it? And I can go back and look at that just by clicking on that link. So it's a handy little tool. And if you wanted like the version you have on your own computer, you could literally like roll it back and work on it in RStudio from that particular point in time, if you wanted to look from an older version. I don't know of any other software that can let you do that. So I think that's very powerful. Like I often will write papers or reports using R Markdown, and there might be different versions of that paper that I want to save or go back to in time. And I can revert to those if I wanted to, as opposed to just saying like, you know, get into that trap of saving it with a new file name each time. And I don't know where that file came from or which one I was working on at that point in time. So this sort of saves you that headache of trying to, you know, get in that infinite loop of multiple files.
Yeah, as we were preparing for this workshop, One of the questions we wanted to ask the group was if anybody is doing our Markdown to write papers. Has anybody had experience doing that?
Yep. Yeah, the last paper I wrote, I used our Markdown, and it huge help. A little bit costly on the front end, but each of those little changes were so much better.
Yeah. Well, that's a very important point. Is there's a bit of a cost with every one of these tools. You'll feel like you're clunky and not adept when you first start using these things, and that's normal. But I think the important thing to realize is that learning these tools is an investment in the future, because there's a bit of overhead, but you'll quickly find that how did I ever get by without using them? I can't imagine my own world, my own career without using Git and GitHub and R Markdown. It would just be a living hell, to be frankly. So hopefully that's kind of clear about what Git and GitHub provide, how version control can make your life easier from just organizing your own workflows. The other part of this watch and learn I wanted to get into was project management. And so the setup I showed you is kind of more on the personal level of creating your own project in RStudio, using your own GitHub account. But how would you use this to work with others? If they're using Git, if they're using RStudio, it's a breeze to sort of work together on your own repository, because you can have multiple users on GitHub. They can pull down the version from the cloud and work on their own computer, push up to it, changes they've made. You can pull those down on your own computer, vice versa. So it's very simple, but you oftentimes run into this scenario where you have a colleague that doesn't want to use Git or doesn't know how to use Git, or they've never seen R in their life. How do you get them to sort of use these platforms? It's a huge hurdle when we sort of talk about these new tools. So there's a way to do that. And I want to walk through an example of a particular problem that we had recently, or challenge rather, at the Estuary program. And so I'm going to go to our webpage.
While he's doing that, one of the hurdles too that you might run into, especially if you're in a large organization, is just being able to get access to some of these platforms. I know in preparing for this workshop, I ran into a bit of a hurdle trying to get Git on my work computer, because nobody here has used it before. Now we have RStudio and that's readily available, but I'm having to sort of introduce this organization to what we just talked about. So this is an institutional change or leap, if you will, as much as it can be as at the individual level.
Yeah, as an advocate for open science, it's easier for me to evangelize about the value of it, but there's always hurdles, as Chris mentioned. And I think it's useful to understand how to address the hurdles, but also realizing that you yourself are a powerful agent of change to try to convince people that these are worth adopting. And the first hurdle you might have is an IT hurdle, and it's oftentimes the burden is going to be on you to work with IT staff to develop a workflow for onboarding this new software, or making them comfortable or aware that this is something that is safe to use. It'll actually be an investment in the future, that sort of thing. Because without everybody sort of trying to push in the direction of more open science, it's not going to go anywhere. So I'm just sort of again trying to motivate you all to think about that as agents of change, that you can sort of take that responsibility. So the example I want to show you is this is our webpage of the Estuary program. We have this report that we put out every 3 years called State of the Bay. And it's basically exactly that. It's sort of this comprehensive high-level public summary document that reports on how healthy the Bay is, hitting on all different aspects of it, from water quality to habitat to public outreach, all that fun stuff. And so we've been doing this for many years. I've only been here 2 years, so now I'm trying to think about how we can do this in a more open environment. But we actually went through the process of revamping our website last year. So this is what you're looking at now is our new website. And we knew that this state of the Bay was an issue from a time investment and the reproducibility aspect of it. Each year we knew, or every 3 years, we knew that we had to gather the data, summarize it, and put it up on this platform. And it was just took a lot of time. And so we knew this was an issue and we were developing the website. We kind of were like, this is a placeholder for now. We know we're gonna have to do a better job at synthesizing the data to populate this report. And so this is kind of where we landed. We have 3 sort of strategic goals of the program. We want to work towards clean waters and sediments. We want to work on thriving habitats and abundant wildlife. And we want an informed, engaged, responsible community. So like all the things about the Bay, basically. And so our State of the Bay report describes different indicators, if you will, about these three strategic goals. And so if you go to the water, the clean waters and sediments, you see there's different tabs you click on about water quality, or total nitrogen, or tidal creeks, that sort of stuff. Now, this is an improvement over what it was on the previous web page, but where this kind of falls short of really being truly open science and reproducible and transparent is we put together these kind of static documents, these PDFs that were, I think, a valuable resource for the public in terms of understanding what the state of the Tampa Bay Benthic community was. But it was really kind of a disservice for us at the estuary program because these are not reproducible documents. These are things that we had to put together by hand. These are static PDFs that, I created, or I think this might even be a snapshot from a PDF, this little index report card. I know this definitely is, but it's sort of cobbled together from different places of, on our network drive, and sort of putting it together, it was very tedious. And so moving forward, our next State of the Bay is going to be hopefully created by April next year, but we wanted to do this better because we knew that this was time intensive, prone to error, took a lot of time to put these little PDF summary documents together. So I took this upon myself to say, let's do this better internally. Let's use open science platform to do this. And so what I did was, as a starting point, I basically said, everyone in our office, we all know the subject matter behind these different strategic goals. Let's just start with reviewing the text in these documents and then using that moving forward to create a more living document that has integrated text with code. It's producing the documents all in one place. It's serving it up on a web framework like an HTML file, and then populating this web page without us actually creating these PDF files by hand. So it's still a work in progress, but I want to show you how we are working towards that more open workflow, that more efficient workflow using some of the tools on GitHub. So like I said, I'm the one usually working in GitHub through our organization, but I saw this as an opportunity for us to all work together on GitHub in our office, all of my coworkers to build this in a more collaborative environment. So I will go to this State of the Bay repository that I created, which got to go to the Tbep page. So again, this is our group web page here. State of the Bay is here. So I made this repository, and I set up a set of issues in a project board that we can all work on with different tasks assigned to each coworker of mine to review the text documents, make sure that we're actually setting it up in a way that can feed the website moving forward. So I set this up. I'm the one that uses Git. So I did the back end work for this. But then what I did was I made this project board called copy editing. So again, this was like the first step towards us working together with the documents. But I set up this project board. This is a Kanban style. So you can do this in GitHub. Basically, you can create these different columns that describe where you're at in the project. So this is things for people to do. These are things that are in progress, and these are things that are done. And so each one of these columns is populated with cards that are specific tasks that I assign to each person in my office of, review this part of the document and make comments and make changes. Now that might not make a lot of sense, but I'm trying to like bring it all together to show you that this is the Kanban workflow you can use on GitHub. But how this actually worked in practice is that, like I said, no one in my office really, there's one other person that knows how to use Git, but I basically set up the documents along these sort of thematic ideas, right? So this is a clean waters and sediments file, right? So this is the text I wanted people to edit. And essentially I looked at the file and I said, okay, well, just to pick on Gary, he's in my office. He knows about the Tampa Bay benthic index. So I wanted him to review this subject matter, this text in here, to make sure that for the next report, it was up to date, had the most current information. So I right-clicked this and I said, reference a new issue. So this goes to the issues pages, which is a place for us to basically say, this is something that needs somebody's attention. This is very common in software development. But for this example, this was my place to say, review content on benthic index. Now, this is a link to that particular line in that file. I'm going to assign it to myself, actually, because I don't want Gary to freak out. He's going to get an email if I do this right now, but I'll assign it to myself and I'll say, review this material or edit this to make sure it's up to date or whatever you want. So I'll submit this issue, right? And then say, I assign this to someone else, they'll know, they'll have to review this. They'll go to the project board, and so they can track it this way. I actually need to add this, so I'll add the card. So I'll just move it over there. Now this is in the queue to be addressed. Okay, so this is kind of more about project management, but what's cool about this is this now, if you don't understand how to use Git or RStudio, you can actually start doing version control in the browser. So this has been assigned to somebody. They can go to this issue and say, oh, I need to start editing this line, okay? So that was linked to where they want to start documenting this, and they can actually literally do this editing within GitHub. So they can actually click this, they can click this little pencil up here, top right, and start editing the file. So now it's in kind of edit mode, and I can start making changes. So since this has already been reviewed, I'm going to put something here that I'll actually remove later, but I'm just going to say this is like an edit that somebody needed to make. I just added some text, whatever. It could be like more detail about the benthic index, who knows, but I just added it. It's a change I want to commit, whatever. I can then say, made an edit that was needed. So this is like, again, the commit message that should be more descriptive than just made an edit, but it should sort of describe what the changes were made, so that if someone's looking at that history, they know what has happened in that file over time. So then I commit the changes. It's now committed. It's in, actually, if you go to the commit tree or the commit log, you'll see that it's added on top of there. Done all through the browser, so you don't have to mess with RStudio. Actually, everyone in our office was using it this way. Like I said, I myself and only one other person know how to use Git in RStudio, but we had 7 people in the office all editing these files this way on GitHub without having to understand how to use RStudio. And so going back to the project board, I had to remind them that, oh, hey, this was assigned to you, you need to do this. But once I reminded them, they started moving the files or moving the cards, the issues from to do to in progress.
So that's an important thing to keep in mind. It doesn't automatically move. You have to move it.
There is a bit of automation. So like if I'm in this issue and I was done making the changes, I was satisfied with it, I can close the issue, and actually in this case, it automatically moved the card to the done column. So again, the details of all this, you don't really need to understand exactly everything I just did, but just understand that you can use this workflow with other people that might not be comfortable using RStudio or Git, then actually make them part of the process, actually have them be part of version control without them even really sort of knowing it. And so where this is going is that now these are our Markdown files that they've edited that I can actually start populating with our code that I can sort of knit and make into HTML files that are going to go on the website. But that's a little bit beyond the scope of this workshop, but that's kind of my vision for what the State of the Bay report will be. And this has all been information that's been contributed to from multiple people in my office. So.
Any questions on this? There's a lot of information there. And you know, obviously, it's something that I would encourage you guys to try if you haven't already done so. Play around with it, and I think a real world example like this one is important. I don't know exactly how many hours doing it this way has saved you all, but I know because I was involved in some of the early work to develop these report cards. There's a lot of manual labor that went into it, many hours, and that has now been largely automated through this process.
Yep. And the name of the game is saving time to make sure that we're being more efficient and working towards a better product that way. So.
All right.
I have a question.
Yes.
So two questions actually. So first, when you were working on just the text, you know, not our Markdown, but just everybody in your office could edit the text using GitHub. Was that a Word document or a .txt, or like what kind of file format had you uploaded to do that?
That was just a Markdown file, which is kind of similar to just a regular text file, except it's got a few extra features. So Markdown is kind of like a very lightweight version of HTML with, it lets you do minor formatting of web content using very simple things like how do you make a list with just text markup, or how do you do referencing with simple text markup. It's like I said, it's a lightweight to create web pages. So the thing about version control is it works on text files. That's how it literally compares line to line. Those principles kind of translate to say like CSV files or other files that can be put in like a simple text editor. Because it's just based on a reference between two things. The way your computer works, it just reads line by line. So it can't say do version control for like a docx file, because that's like a proprietary binary format that is, you know, it's very hard to sort of disentangle that into a nice text file format. Most doc files on GitHub, it's impossible to do version control on them. Is that kind of what your question was, Jonathan? Like, can you do version control on doc files or just like text files?
Yeah, like what's the best file format to upload to do this on? I guess is the question. Yeah,
it's going to be the best one. But GitHub has a lot of nice features too, like the Markdown files. You'll see that when I was showing you the files themselves, when you click on them, it kind of looks like a web file. So GitHub has these things when you're actually looking at it at the web browser, it actually renders it as kind of an HTML file. But if you wanted to look at it line by line, like as an actual text file, you have to go to this this guy, display the source blob. So literally the source file that you're looking at. And this is like line by line. And that's just kind of the convenience that GitHub does for you to display the file in the web browser. But if you're doing version control, you're doing editing, you're doing it on the raw text file. So like what I was saying about Markdown is like this little pound sign. This is Markdown for like different headers. So this is like a level 1 header. This is a level 2 header. And if you looked at this in the rendered version, that's what it looks like. So Markdown, like it's a lightweight version for formatting pages in a web environment.
Okay, yeah, that's great. Thanks. I have one more question. I just maybe this is not important, but I noticed that your username or your avatar or whatever, it wasn't your actual name in GitHub. Is there any security reasons why someone might want to do that, or does it really matter? You know, if you have like your face and your picture and your name and all that.
Well, I guess it's just as open as say something like Twitter. You know, anybody can Google my name in GitHub and they'll find me. I mean, it's like any other social media. I mean, it's not social media, but it's the same idea where you create a username. I believe every user has their actual name below. I'll pick on Maya. So she picked MCB, which is very clever because that's her initials, MCB, but then her name is right there. Yeah, I mean, like I said, if somebody Googled Maya and GitHub, they'd probably find her. So if you have a problem with that, then that's, I guess, maybe your comfort level of putting yourself out there. You don't have to put an avatar. You could, there's like user generated ones that the system grades for you, but yeah.
It's also a way to make it smaller. Like my name's really long, so I think mine is Wet Photon 1, just because it's shorter than all that.
Yeah.
Yeah, that's me right there.
Yeah, so here's Chris.
Oh, just Wet Photon, yeah.
Well, your name is on there too. So.
Right. Yeah.
Yeah.
Does that's I think that's your point, is you can put whatever you want as your username, but if you click on it, it's going to show you your name and information.
Okay. Yeah, that's great. No, thanks.
Mm-hmm. All right. So let's see, we got about
we're
25 minutes.
Good. Yeah. Do we want to take a quick break and finish up, or try to get through this section? I think what we're going to do is, I think we've got one more watch and learn. We're going to talk about data repositories and talking about metadata and what that means and why that's really important. Although I'm sure everybody here knows fundamentals of what metadata are, and we already talked about it too. But there are certain data repositories. I don't. Do we want to take a quick break? I mean, whatever y'all want to do.
Yeah, how you guys feeling? Power through it.
There is an exercise at the end of this, actually. So maybe we want to take a 5-minute break and then pick it up. Okay. So what is it now? 4:19, 4:20. So be back in about 5 minutes. All right.
review that offhand, then maybe something separate that then can be say, okay, you're saying here.
All right, well, I guess we're all back now. So we'll just keep trucking along. I did want to briefly address Robert's question in the chat about working collaboratively on a research paper in R Markdown. You know, any suggestions or ways that can be done more efficiently if it's been done successfully, I guess. I'll say from my experience, I've done it. It's always a challenge because, as Robert points out, you will always have colleagues that just don't use that platform. It's the exception, or rather that's the norm rather than the exception. Very few people are actually using our Markdown now, at least I think in our discipline. So you'll have to work against that. But as I said before, I think the more we try to advocate and push for these tools, the more people will realize the value that there is in investing in them. But one specific thing I wanted to point out is that the example I gave you about the State of the Bay earlier, where I had different issues and the project board assigned to different people in my office, I actually use that same approach for a paper that I've been working on now, where again, there's 6 out of 8 people in my office that don't use Git or R Markdown, but I said, hey, I would really like you to review this paper. Can you go to GitHub and review the R Markdown file and just make your suggestions through the web browser? And all of them did that, and it saved me a lot of time from, me sending them a Word document that then they do track changes on, and I have to transpose them to our Markdown, which is doubly redundant. We want to avoid. So I still think there's value in using GitHub as a platform to try to work together, especially with people that might not be comfortable using RStudio or GitHub, or Git rather. So that's my optimistic path forward for how to do that.
So I've added an additional computer so I can monitor the chat. So that was my bad. I was on this side of the room. So Robert, I didn't see your question, but now I've got, we're good now, I think.
So we can do this 3.
Yeah, apparently I can be at 2 places at once because I'm logged in on the other machine as well. All right, so we are going to continue. We'll finish up section 2 here by talking about, let's see, we're still in data repositories.
We're on data repositories.
Yeah, we're still on data repositories. So again, when we talk about data repositories, we're basically talking about where you store your data, and more importantly, how the data are interconnected. So this whole idea of an online network of connected repositories is really important, because you have to be able to kind of link data from different sources. Some of you, I'm sure you've used at some point in time, data that are collected by various agencies. Here in Florida, for example, we have a standard database for water quality data that, at least hypothetically, if you are a public agency and you're collecting water quality data, it goes up to a central repository that anybody is supposed to, in theory, be able to access. And it works, I think, for the most part, assuming that people are uploading their data to that repository, which is a really important consideration when you're talking about repositories, and you as an individual or as part of a program are trying to determine what repositories should be used or would be more useful for you. There's some limitations to the types of data repositories. The example I just gave you in terms of like a state network, those of you who are familiar with the EPA's STORET network is another example of that. Is it really a repository in the open science sense of the word? Maybe, maybe not, but it's maybe one step towards open science, where you're really just taking the data and housing it somewhere, but you're housing it in a place where others can get access to it. I think in the spirit of open science, what we're really talking about are more repositories that not only allow you to upload your data, but also allow you to manipulate yours and other people's data. So there's 3 examples on the syllabus that are more what we would consider domain specific. So you have the knowledge network for biocomplexity, HydroShare, and OPC. I'm not that familiar with any of them. I've kind of, in preparation for this workshop, I've kind of looked at all of these, but Marcus, I know you've had some experience with all 3 of these.
Yeah, I think the main point of just presenting this idea of data repositories is to know that they exist, and they're a resource that you can use to extend the life of your data beyond the project, especially when we think about the FAIR principles. I mean, these are places where the data can be findable, accessible, interoperable, reusable. So they're definitely an underutilized resource. I just wanted to just briefly show the Kmb Archive. This is one that's created through UC Santa Barbara, and it's more commonly used for ecological data sets of the more conventional theoretical ecology. But I've posted data sets on here, and they're not sort of restrictive by any means. But I just want to show you like what's super cool about this is, you might ask yourself, why should I put my data on a repository? If you go to search data, you see like a map like this that basically on the right here has a number within each grid cell of the number of data sets that apply to that particular region. So if you're interested in, what are some cool data sets for the Gulf of Mexico or around Tampa Bay, you could zoom in and sort of
look at things from a geographical perspective. Now, this might not seem valuable from like your perspective if you're pushing data up to Kmb, but think about like your future collaborators. Like if they found your data set through this venue, you know, it's going to have metadata associated with it. It's going to have your name on there. So they know that, you know, oh, say Marcus created this data set. Here's this contact information. I want to work with him. He can be a collaborator. We can work together on this data set. We can make this data set something more than what it was for the project that was used to create the data set in the first place. And so this, when we talk about open science, is a valuable, like really valuable tool for just making sure that happens, because it's like, you know, the data doesn't just serve in the purpose of here's the paper, it's done. This is a place for it to live on further and actually make you hopefully identify or work with collaborators that you wouldn't have worked with before. So that's my incentive for using these tools.
Yeah, there's several reasons to use tools like this. And again, this goes beyond just a place to put your data. It's a place to encourage collaboration across, you know, divides that otherwise wouldn't be possible. So with that, we're going to kind of talk a little bit now about this whole concept of the code of conduct. And, you know, anybody who, you know, everybody who signed up for the conference knows that you had to click on a box that says, I agree to the CERF code of conduct. And there's a whole website. I'm sure everybody read it diligently and memorized it. But it's really important. It's really important because as you collaborate, you know, there are different opinions. There are different, you know, reasons for doing what you're doing. So code of conduct is really important. And it's essentially, you know, a set of community and social standards and with a common goal. So there's work that needs to be completed, and it's a way to ensure that that work is done in an effective and efficient manner and within certain bounds. Those of you who are, you know, either from previously or currently in academia know that it can be challenging sometimes to work in collaborative environments. I mean, it can be in any situation. So a good start when you're thinking about open science, when you're thinking about how do I apply open science in my own collaboration space, is to think about creating a code of conduct. There are some other examples that are offered, so you can, you know, certainly go. I don't think we have time to kind of delve into, you know, the various types of code of conduct. Like I said, if you want, you can look at the CERF's code of conduct, which we all agreed to be here today. But we do have an exercise, and I think it's a good exercise and a discussion, really more of a discussion, I think, which is the idea of developing a code of conduct for your group in this idea of a shared workspace. So there's some questions, and so really what we want to do is just kind of explore some of these and get kind of your feedback on, you know, what you think are, like for the first one, what are some of the reasonable expectations for the various group members? How is inclusion defined and encouraged? How are similarities and differences recognized, and how will conflicts be managed? These are all really important when you're trying to create a productive environment. Anything to add to that?
No, I'll admit that code of conduct is something that's fairly new to me as a concept, but they're definitely really important for, I guess, it's a social contract for how we all sort of work together. And you can't talk about open science without talking about codes of conduct, because you want to make sure that when you are working together, everyone feels like they have a vehicle by which their voices are heard, their feelings are respected, and if there is conflict, there's an avenue to try to resolve that conflict. And it's just a way to be like, it's transparency, I think, you know, a big important concept of open science is being transparent. And this, you know, might not be transparency from the perspective of, say, developing a piece of software, but it's transparency from a social perspective, which I think is equally, if not more important.
Yeah. And I think, you know, some of these, some of the elements of the code of conduct too is going to be dictated by whatever organization you may have to work with or for. For example, if you're like here at the Water Management District, if you're putting together a web product or a tool, I'm sure it's true with you guys as well, it has to follow certain ADA requirements. So there are certain forms of inclusion that have to occur in order for us to be able to publish a product online or a tool digitally. So those are some of the things that have to be hashed out, and the sooner you do that, the better, because then you don't have to deal with the last one, which is conflicts, and how you're going to manage that.
Yeah.
But I'm curious, so I guess I'll just pick on somebody. So Amin, you work kind of similar with a similar organization as I think I do at the Water Management District in Florida. We're a little bit different, but what are some of those reasonable expectations, I think, in your setting, where you were, that you would expect to see in a code of conduct?
No, I'm pretty new to the Water Development Board, but I think we have some stuff that we want to share, but the problem is we're not all at the same level. I think that's the main issue, that when we want to we want to set some expectations for like how we want to move forward, because we are not all at the same level and we are not coming from the same background. There might be some issue. We might see some resistance, specifically from those folks that are old-fashioned and they just want to work on in a very isolated situation and don't want to share anything with anyone, even though they're working on the public sector. But they said, oh, it's my code, it's my data, I'm gonna be in charge, because they see that as a threat if someone else could enter that territory and then do what they are doing. So they feel that, oh, if someone else could do what I'm doing, then what do they need me? I need to be unique in that regard. So I think that's one of the main challenges that I've seen so far.
Yeah, definitely. I think that is a big challenge. And Marcus and I were talking at lunch about, we're at a time in the workforce where we're losing a lot of people to retirement, to, just through folks that have been doing the job for a long time and have been doing it a certain way. And you approach them with new tools and they don't want to do it. And so, the expectation is that, we're all going to sort of learn together, but there is that pushback, and change is hard for everybody.
Yeah, believe it or not, even in the past months, I had to have two very tough discussions. One about moving from Fortran to Python, and the other one was moving from saving output files as text file, moving towards NetCDF rather than text files. So, and you don't believe how much resistance I get.
I believe it. I definitely believe it. I remember when cloud computing started to become common, and we have OneDrive here, and it was a big deal just to do that, to where,
yeah.
You mean my files aren't, they're going to be up in some cloud somewhere? No way. That's not how I do. I have a hard drive here, an external drive, and that's where everything sits.
Yeah.
But now everybody does it. So it's changing. It's a challenge, but I think that's where a code of conduct is important, because you don't want to just discount somebody because they're just set in their ways.
Yeah.
Maybe they have a point. I don't know. I mean, I like your point, to the idea that there are people that are they're reluctant to share because they're afraid that somebody's going to take their data or their model or their code and do something better with it.
Yeah, that's one of, if not the top point of resistance to open science. And I don't know if now is the time to have that discussion, because I have some opinionated opinions about that.
Yeah, but I just want to add this, something that you mentioned earlier is very important. You said even with being very generous, in the next 10 years you might not work with R, right? But that scares some people to death because people used to make a career out of knowing Fortran. People used to make a career out of just know how to do C++ or whatever. And now it's like everything is changing and they are not comfortable about that. So,
well, I'll put it this way. I've made a career out of using R, and I'm 100% anticipating the day when that skill set is no longer relevant. But I've seen in my 10-year career to date, people where in their time they were, say, the master of SAS, and SAS is still used, but I think it's definitely not in vogue as it was in the day. But I've seen people twice my age transition from SAS to R, and now they're like the go-to expert for using R in their little circle or larger circle, whatever. And so I think the key idea in all this is like anticipate the day when your skill set might not be relevant and be aware of that, be ready for that, and be flexible. I mean, that's really important. The one thing that's a constant in this world of open science is change, and realize that you're going to have to adapt to new platforms when they become the more improved version of whatever platform you're using to do work. And so just one, being open to that concept, and two, realizing that, yeah, it's going to suck when you have to change that new platform. Yeah, you're going to be less efficient. You're going to suffer in your productivity, but know that if you want to keep being relevant, if you want to have, if you want to stay competitive, I guess is maybe not the right word, but if you want to stay abreast and make sure that you're on top of the wave, that setback is temporary, but you're going to poise yourself for hopefully a more productive future than just being sort of an antiquated person that just knew this one thing and that's all they do. Yeah, just to, kind of bring it back to the code of conduct. This is a way to sort of set those expectations forward. I don't know what the lifespan of a code of conduct is, but if you can at least be vocal in terms of what people are expecting if you're going to work in this collaborative environment, that's a way to sort of maybe anticipate those challenges and put them down on paper first, so that when they inevitably come up, you have a way to sort of address them.
Yeah, and since I'm new to the idea of code of conduct in this context as well, would you say, Marcus, has it been your experience like using GitHub and sort of you were showing that Kanban board and assigning tasks? It seems like when you're developing that expectation through your code of conduct, that there's got to be a gatekeeper. There's got to be kind of somebody, at least at first, that can help facilitate that open science environment. Otherwise, yes, in a mature sense, everybody's fluent in the technology and the tools and are doing everything they need to do. But we all know that doesn't happen. There's tasks that are given out that aren't completed. So somebody's got to sort of be there to sort of keep the cart moving, don't you think?
Oh yeah, absolutely. That's kind of my role and my job is, at least when it comes to this open science stuff, I'm the gatekeeper, and that term kind of, I think, makes the hair on the back of my neck raise up a little bit, because it gives me some responsibility that maybe if I wanted to take advantage of it, I could, if I maybe wanted to. Not saying I would, but what I was thinking, with the code of conduct is to sort of get around that, where if someone's seen as a gatekeeper or like the bottleneck, if you will, the code of conduct is a place for not just responsibilities of the people you're working with, but responsibilities for me or the other gatekeepers or your administrator. It's a way to make everybody accountable. And I think that's what's really powerful about it, is in order for it to work, everybody has to buy in to this idea of a code of conduct, no matter where they're at in the institution. It's not like the boss is writing this code of conduct that says, this is what my employees have to do. That's not a code of conduct, because that doesn't make accountability to the boss or the gatekeeper, the bottleneck. It's meant to be inclusive of everybody. And that's, I think, where the real value of this exercise comes into play.
Yeah, and I think that's important that's an important point, because we're hoping, and sort of one of the things that we're trying to do is get you guys excited, if you're not already, about open science and what you can do to further advance this concept in your own organization. So you may be that person that sort of is the facilitator, but that doesn't mean you're necessarily a manager or a supervisor, or you're the one that's in charge. So there's a very clear distinction between, who will be all right, I won't use the term gatekeeper. I've got to come up with a better term, but the person
Who's the motivator?
Yeah, that's a good one, right? Who's the motivator that's going to say to people, get excited about this. This is going to work out. Trust me, it's a learning curve, but we're going to get there. So it is important to think about what your code of conduct is, because you can probably appreciate that the lines of the hierarchy of an organization might get blurred a little bit in terms of who's kind of pushing open science in your organization relative to who's in charge, so to speak. So, all right.
So we're at 4:45. I don't know if you want to quickly wrap up on the.
Yeah, I think so. Let's wrap up this section because we've still got a good bit to cover. We're about at the halfway mark. I'm not going to spend too much time about tools for collaboration because we have kind of spent a good bit of time on GitHub, and Marcus, kind of took us on a tour of it. But what we wanted to do is we did want to let you all know that there are other tools for collaboration out there beyond just GitHub. And many of you may have experience with these, but Slack is one of them. And you can go through this at your leisure and kind of delve into some of the pros and cons of each of these. Trello is another popular tool for collaboration. Again, it utilizes this Kanban style of workflow organization. Google Drive is one I know, working with the SRA program, that you guys use that on a daily basis. So I've been plugged into it. Google Drive is a little bit tricky for some in the public sector. I know my organization at the Water Management District does not use Google Drive for certain IT security reasons. But my experience with it is it's a great platform. And so, if you can use it, it's a good one as well. Office 365 seems like what everybody is going to. That's what we use at the Water Management District. Again, it has its pros and cons. One of probably the biggest con for Office 365 is you need an account. So, if you are a grad student and you're at a university, hopefully you can get, an account through the university. I know that at USF, and I still have an email account active at USF, University of South Florida, they're transitioning away from Google and going to Office 365. So a lot of organizations are making that switch. And then, of course, GitHub, we kind of talked at length at that. So we did have setting up a project management system. We kind of did that, so we don't need to do that again. And I think that should do it for that section, unless anybody has any questions. I don't see anything in the chat, but if anyone has any questions, feel free to unmute yourself at this point before we kind of wrap up section 2 with managing expectations. And we've already kind of covered this section, so I don't think we really need to go into too much here, other than really that second paragraph, which is really important, and which is that these changes aren't going to happen overnight. I talked a little bit about STORET, the EPA water quality database. We have one in Florida. Every state has one. There's a continuum from working in a silo in a windowless locked office to true open science. And if you're anywhere on that continuum, you're doing good. So it is a sea change it is happening, though. I think it's safe to assume that these changes are happening. Ours certainly has been a big push in that direction towards open science, but it takes time. So we're trying to break free from habits that have been entrained for generations, and it's going to take some time. So yeah. And again, the final thing here is that tools are temporary, and so we have to think about it that way. that what we're using today likely won't be what we'll be using tomorrow. Yeah. So. All right, I think that wraps up section 2. And we're going to move on now to third section, which is open science for impactful products.
Any questions about any of that before we move on?
So I need to leave, but I will be back probably by probably in half an hour or 45 minutes. Are you guys recording this session?
Yes, it's being recorded.
It is being recorded.
Okay. Okay, so I'll be back in 45 minutes. Thank you.
Yep.
Mm-hmm.
Let's see, I had a couple points I wanted to mention about the platforms before I moved on, but I think I'll skip them in the interest of time. Okay, so this is the third module of our 4-module course. So we're just over the halfway mark. The last module was all about collaborative tools. You know, open science is all about collaboration, is kind of the, you know, single most important thing that can be enhanced through some of these platforms that we're talking about. But we're kind of going to pivot now and sort of, you know, go in the opposite direction and talk about how we treat data in the open science perspective as another very important activity that can really improve how you work towards these applied research products that I think we all are hoping to produce through open science. So what we're going to do is talk about best practices for data management. And this is where I get really excited because I wear a data scientist hat that I claim to be. And so I think a lot about how data are treated as a resource, not just something that serves an end of, say, like a paper. And I work, you know, when my daily job, I'm writing scripts in R, like majority of the time. So I work a lot with data, and I've seen, you know, all sorts of examples of how horrible data management can just lead to massive headaches, my headaches, your headaches. And there's just ways we can think about curating data, not just structurally, but how we document it and describe it to make sure that we can, say, put it on a place like a data repository so other people can find it. And hopefully, you know, that's your next collaborator. So your motivation now is to think about data as a living shared resource, not just something that serves an end. It's something to be respected as, you know, not just for the project, but beyond the project. So I like this graphic because, you know, if you ever read any data science book, you'll see the data sets in the tutorial are just like super easy and cute, and like they're in a nice format and they make sense. You can look at the data and understand exactly what it is, but any data set in the wild is you know, not going to look like this cute puppy. It's going to look like this guy here, unless, you know, you're working with somebody that understands data structures and they respect it in a way that is following some of these best practices. So I actually pulled this material from a data management SOP that I wrote for the Estuary program. And I wanted to preface, like, again, you know, what's the motivation for open science? What's the motivation for data management? Why should you care about this? And I wanted to preface this section with like some scenarios that I've lived more times than I care to imagine that made me really care about data management as a practice. Because if you're not, again, caring for your data, you're not going to be able to collaborate. I was also going to mention earlier that, you know, data are like the currency that we have as scientists. And if we're not, you know, curating our currency, we can't collaborate effectively. So think of it that way. So anyway, like 3 scenarios that I've come across many, many times again. And this happened in previous jobs, not so much my current one, but collaborator calls you on the phone. They want a historical data set from an old report, say from like 1995. That's like a nightmare scenario, but you spend several hours trying to dig up this data set. You eventually find it, but there's like 0 documentation for this data set. You don't know what the heck it is.
you don't know what was going in to produce this data set, and you just say that's what they wanted. You send them the data set, knowing full well that they're not going to understand that context, especially if you can't understand it. So they're probably going to use it in a way that was not intended in the first place. So that's nightmare scenario number one. Just people requesting data and you sort of trying to dig that stuff up and wasting time in the process. Second nightmare scenario is you, and not to sort of pick on contractors, but I've seen this happen a lot. If you contract a project and you get a deliverable for a data set that's stipulated in a scope of work, this comes in multiple different formats, often a proprietary format, and you basically can't verify the information because it's not documented, it's not reproducible, and this erodes your faith in the final product, but also any kind of decisions that are going to come from that data set product. So that also speaks a lot about the ability to update those results in the future. So oftentimes, you know, contracted projects are one-offs, but if you want to keep building on that data set, you know, how do you do that in a meaningful way if there's not a clear workflow that went into producing that data set? This third one is actually something that I feel like is my duty and my job that I'm trying to solve. And this actually, we have an annual report card that we produce every year for the estuary, the Tampa Bay Water Quality Report Card. And I'm going to pick on my colleagues now, but they had to produce this every year. And this was something that, you know, was created through a workflow that was just basically a bunch of SAS scripts on one person's computer that they had to run every year. They had to go to the website or, you know, even call somebody on the phone to say, can I have the data for this year? And then run it through this workflow and my SAS scripts and create this new static PDF that we disseminate to our partners. And so this was by no means an efficient process. It was not reproducible. And basically they wasted a lot of time every year creating this product, which was a great product because it was a good public summary document that distilled the results in a way that was digestible, but how it was created was very inefficient. And so actually the example I was showing you earlier with the software, the R package that we were going over on Git, actually encapsulates a lot of the workflows for that report card so that, you know, each time the data get updated, we just run the routines, creates the document, no problem. So hopefully you're scared to death about these nightmare scenarios and hopefully can sort of appreciate how you might want to move forward with better data management practices to avoid these things. So like, why do we get in these situations? Data management is a pain. It's tedious. You know, I think people tend to not appreciate the fact that when you're recording data, how you record it is not like the easy way when it comes to like analyzing the data. It's not in a tidy format. Like if you're recording data in the field, it often gets entered into a spreadsheet into that same format. And so that's oftentimes how data can be convoluted. Excel is also kind of a problem. I don't want to pick too much on Excel, but I think it's, all right, I'm going to pick a lot on Excel later, but it's used a lot as a data management system, but it's not data management software. I'm not really even sure what it is. It's kind of a graphical user interface for like analyzing data, but like in this weird cellular format, I guess.
It's the digital version of a ledger.
Yeah.
Like the old ledgers that you had like on the, you know, you see in the Christmas Carol where they're like scribbling numbers, and that's what it is. I mean, it's just a place to store numbers, really not manage the data.
It's certainly, I'll say it's clever software, but people use it as a data management system, and it's not, it has a lot of tools that promote bad habits that I'll talk about in a second. Actually, in probably about 30 seconds. And then the last one is just metadata as a chore. You know, we'll talk about metadata later as information about information, essentially, but metadata is your gateway to data repositories. If you don't have it, you cannot upload your data to a repository. But no one likes doing metadata. It's an afterthought. And the value of it is not apparent when you're doing it. So for those reasons, people don't document their data sets.
But fact of the matter is, if you do think about data management practices in terms of tidy data structures and what is going into your data set, you'll make your life a heck of a lot easier. And it's one of those things that the investment up front might seem like a pain in the butt, but you're doing yourself a favor, you're doing your colleagues a favor by doing your due diligence with data management. And the FAIR principles will really go a long way too when you think about data management. So oftentimes when you think about findable, accessible, interoperable, reusable, that speaks directly to the data itself. The data repositories are meant to support the FAIR principles. And if you're doing data management, you can achieve all those principles in one fell swoop, hopefully.
And I can say that over the years, I've seen an improvement, at least from a public organization standpoint, in managing metadata and populating metadata. At our organization, we often have a very strict set of requirements. Even if we contract with consultants, they're required to meet certain requirements for data entry, and metadata is a big part of that. We collect a lot of imagery for seagrass mapping, and there's about a 60-page document that sets the requirements for how you do it and what you do with the data. Now, one thing I'll add too with metadata is that in some cases you can, and I would think in all cases, you can automate the checking for metadata. So we have certain routines that we can run data that we get in-house to check and make sure all the metadata is properly filled out. And that does actually save a lot of time because, like Marcus said, nobody wants to read metadata until they have to. And if you have to and it's not there, that's a real pain. So being able to potentially automate that process could save you a lot in the long run when it comes to making sure that that metadata is filled out.
Yeah, and the sooner you think about metadata, the easier it's going to be. So I think, as Chris said, it's going to be more and more common that metadata are going to be requirements for even, say, data for a paper. I've seen that in the last 10 years be a common request now. And, you can always do it as an afterthought. And fact of the matter is, like 90% of the time, that's probably what people are going to do. But the sooner you think about it, the easier your life is going to be. And it goes a long way too, in terms of making your data more tidy, because if you kind of have an expectation for what your data are going to look like up front, and we'll talk about this later with data dictionaries, when it comes to filling out that data or actually creating the data set, if you have a predefined structure that is, in a nice concept in your head, it'll make the data entry a lot quicker. So do the heavy lifting up front and just set yourself up down the line for better metadata. Tidy data is, the first thing to think about with data management, and that'll go towards a discussion about data dictionaries in terms of like, how do we conceptualize data? And then that'll go towards metadata as like in a broader concept of descriptions of a data set. But if you sort of lose the train of thought along that, just think about tidy data as the one take home message from this module. And so data, as I said, I pulled a lot of this material from an SOP that I wrote, and I was really thinking about conceptually, what is data? Data is a lot of things. I mean, it's information, and that could be a tabular data set, or it could be a workflow that's information, or it could be even a paper. A paper could be considered data in like the meta-analysis concept. But for this exercise, it's useful to just think about data as its tabular format of just rows and columns. That's the easiest way to think about data. And so we can store that information in a lot of different ways. The better way to do it is with tidy data, but as we'll talk about in a second,
you can really abuse tabular data using software like Excel that encourages implicitly bad habits for storing information. And so to kind of motivate you of how this can happen, here's another meme. You've probably had this happen where you're entering something in Excel and Excel might think it's a format that you're not intending it to be. This is about dates. We all know dates are a pain in the butt no matter what platform you're using, but you might have had this happen in Excel. I've certainly had it happen in the past, I guess, when I was using Excel a lot more. But this speaks to one particular issue that, you know, Excel can cause when you talk about formatting. You know, automated features, for example, can be one particular problem with Excel. I'll point you to this example here. This is like a running archive of stories, or I guess examples that I forget who runs this. I guess these folks here, but this is like a long list of examples of errors caused by Excel that led to bigger problems. There are some pretty prominent examples where this has happened, but this is like hundreds of examples where it's, you know, automated formatting caused a problem. Where I think there's a very popular one with like DNA sequences being stored in Excel. And this is something I read about, like, I don't know, within the last year, where all the DNA sequences, or some of them, were being formatted with dates because Excel thought it was a date, and that screwed up the entire data set. And people didn't know this happened because it was an automated feature that, you know, the programmers at Microsoft thought would be helpful. In some cases, it probably was, but when we talk about data and science, it can lead to these bigger issues. So
yeah, just going back to the whole concept too of metadata and understanding data. If you look at what's on the screen, this is a European website, so you'll notice that the month and the days are reversed. So if you have a 2/3/2019, is that February 3rd or March 2nd? Makes difference.
yeah, and there's software standards for dates that are readily used by operating systems that handle these issues. But Excel, you know, it's something that they specifically developed to be simple and easy to use. And I understand the issue they're trying to address, because like we're talking about, nobody wants to, well, many people don't want to use open science tools because the tools are hard to learn. So there's a market for easy to use tools, but because they're easy to use and they do a lot of things for you that are meant to be handy, they can lead to mistakes down the line. So I think we all understand that fundamental issue.
I'm old enough to remember Lotus 123.
Oh God. When I was at the EPA a couple of years ago, they still use that.
Oh my.
Oh, yeah. I just had PTSD. Anyway, so that you know, automated formatting is one thing. There's a couple like more subtle things that might seem harmless, but they're still problematic. This is just like a screenshot of one example I found online that just, I'm sure people have been sent a data set that looks like this. And I want to talk about like color coding, for example. That might seem harmless, but that is something that somebody did to the data set that had meaning to them. And that is data. That color coding means something. And unless that's explicit in your data set or the process used to create that data set, that's ambiguous information that can cause problems down the line. It might seem harmless, but it is, I assure you, it's not, because that, you know, it's just hidden information that is not open. It's not transparent what that means, and that can lead to problems. And just the broader issue of like embedding formulas between spreadsheets, that's a nightmare scenario for reproducibility. I mean, like I said, Excel is a useful tool. You could do a lot with it, but if you're trying to piece together an entire workflow from spreadsheets in a single workbook, a lot of people build tools around this. It's crazy. You cannot do it. So I would just encourage you to try to move away from Excel. That being said, I still use Excel for data storage, but I try to follow the tidy principles for storing data. And what I mean by that is I'm not, using colors. I'm only using one spreadsheet. I'm not linking values between cells. I'm literally just entering data in a rectangular flat format in Excel. So what do I mean by that? So rectangular, rectangular and flat, this is your first lesson in tidy data. Rectangular means it's in a grid format, rows, columns only. There's no dangling cells outside of the grid. However many rows you have, they cover all the columns. However many columns you have, they cover all the rows. So rectangular format, and it's a flat file. So no cell formatting, no embedded formulas, no multiple spreadsheets. Everything is entered as an alphanumeric character. That's also really important. Numbers, letters only, or accepted characters that any, the most operating systems recognize. So like, just no embedding in formulas basically. So think about it from the perspective of a computer, or like R, for example. If you're reading in a file, it should recognize all the pieces in that file. If there's a formula embedded in a cell, it's not going to be able to recognize that. So if you can make that file in Excel into a text file that's only separated by commas, then you're doing, for example, you're storing it in the correct format. So this, I also would encourage you to check out this paper by Broman and Wu, came out a couple of years ago. This is another really great paper that kind of really expands on these ideas, like best practices for storing data. And it actually is a lot more comprehensive description of what I just sort of talked about, the pitfalls of Excel and sort of how you can address those issues with better practices for storing data.
So I have a question about, the formulations and not having formulas embedded. A lot of data are derivatives of other data. So let's use total nitrogen as an example, where it's oftentimes it's the sum of your inorganic and your organic nitrogen. So in a spreadsheet, you would have a formula that would simply, produce that parameter. In order to make that data tidy, then you would do that, and you have it written there where you want to take the analysis and isolate it from the data.
Yes, that's exactly what I was going to say.
Yeah, I know. But in the sense that there's always human error in any data collection. So one way to check that would be then to do that calculation and make sure that what's in your original data file, as in this example, TN, was calculated correctly. Mm-hmm. But that would be a separate file from the data that you're keeping in the tidyverse, right?
Yeah, so yeah, I just want to reiterate, like, separating the data from the analysis is really important. Like, and when I think about the work that I do, there's source data, and it should be this sort of tidy rectangular flat file. I almost always never mess with the source data, because that's almost like gospel, pretty much. Like, that's information that someone produced, and if you do anything to it, you're basically kind of rewriting history in a sense. But I think your other question about like simple calculations, how do you make sure they're correct, or what part of the process does that come into play, or QA, QC checks, for example. And there's not really, I guess, a single answer to how that's managed. I mean, there's different tools along the way you can use. One thing I use, for example, is, and this is more of a software development tool, but you can use continuous integration services, which are like automated testing services that actually GitHub has tools available to do that, where you can set up a process where, say you're expecting to get new data sets regularly. You can host those data sets on GitHub, but every time, say, a new data set gets pushed to GitHub, you can say, let me run these routines that checks that, the TN values that are derived from these separate columns meet the expectation based on a formula that I've defined. That's one way to do it. But more from like a perspective of like, understanding the process that went through to creating a secondary data set. And I guess if you want to get technical about it, like a TN calculation is a derived data product, right? Even though it's a very simple calculation, just the sum of a couple things. You know, you could have a separate workflow set up in another repository that has processing scripts that tap into the source, you know, gospel or canon, if you want to use a secular term, source data set that, you know, those scripts that manipulate that or take the data from the source data set to produce a secondary data set. Those scripts then are a process that's under version control online on a repository that then the entire process is there. It's documented in terms of what was done. The script, you know, anytime it changes, it gets committed, it gets pushed up there. And so that way, if someone wanted to know, if like trace the breadcrumbs from, you know, what's this derived product? How is it created? What's the source data? It's all there.
So I think the takeaway from what you just said, Marcus, is that you want to take at this stage in the game, you want to take the data at its most basic and fundamental sense. And you can build in, like you said, the code to do those calculations in your script. But yeah, that's important, I think, because there's a lot of examples of that when you're doing like Grand Blanquet or percent cover of vegetation and you're averaging several quadrats.
Yeah.
You take it to its most basic state and start from there.
Yeah. Yes. Yeah, there's a lot to say about that. Like, what's the most basic state of data?
Right. Yeah.
And, you know, people will probably debate about where that line is. But the reality is with any of these platforms, you could, or with GitHub in particular and version control, you know, as long as you're documenting what you've done to manipulate a data set you send, or even making sure that what somebody sent you is correct. Like you can even run your own checks, as I was saying. If you're doing it in this open, transparent environment, then hopefully you are covering your bases to make sure that, you know, the product you're producing or checking is you know, following the best practices for open science. So, all right, so tidy data, right? So, you know, this rectangular flat file, that's kind of a format if you are going to use Excel for storing it, but there's kind of a structure to that data set that is a concept that I think is really important when you talk about storing data. The rectangular is like a dimensions, the flat file is kind of like what's in there literally, but there's a structure to the data set that's important to realize. And so this is a graphic, and these 3 points describe what this tidy structure is. And I strongly encourage you to check out R for Data Science, which I think is this link down here, Wickham and Grollemund. Yeah, this is a fantastic book. Just it's kind of like my go-to for data science in R that really describes this in more detail.
I think it's open source.
It's open source.
You can get it online and read it.
Yeah, it's
you can buy a hard
really
copy
available
too, but yeah, you can readily view it and read it.
But like a lot of the new contemporary tools in R are built around the principles of tidy data, and it's pretty simple. So the 3 rules are: each variable has its own column, each observation is in its own row, and each value is in its own cell. So that it's not rocket science, but because of a lot of the, I think, hand-holding, or again, what's hand-holding in Excel that they try to make it easier for you, or what's easy to enter data in the field, it's not the same thing as what's easy for analyzing data, can lead to these sort of untidy data sets. And so I think we have an example in a little bit that will show you what I mean by untidy versus tidy, and will be a little more clear. But basically, if you can follow these 3 simple rules, you're doing yourself a lot in terms of setting yourself up for simpler data analysis and easier documentation of the data when it does come to creating a data dictionary or doing metadata moving forward. So the other thing I want to say about that is too, if your data are tidy, it's a lot easier to combine data sets. So, you know, very rarely are you probably working with a single data set. You oftentimes want to say combine station location information with actual attributes about what's going on at the station. And so this is just an example showing, this tidy table 1, this tidy table 2, and how to sort of join them by a shared value or key, if you're going to use a term from database principles, into a combined data set. And this would be close to impossible if these files were not in this tidy format. So this is, again, just kind of an incentive for downstream analysis. If your data are not in a tidy format, it's really difficult to combine multiple data sets into a cohesive format. Any questions about that?
You haven't used the term pivot table, so.
Yes, because that's an Excel term.
It is.
That pivot table nightmare. So like,
I do not like. Does anybody like pivot tables or uses them? Because I don't like them.
I'm glad somebody else said that, Chris, because I hate them, and so many people seem to like them. But
yeah, I mean they work, but to me it just seems like what Marcus just went through is intuitive. It's basic. It's easy to understand. I can't wrap my brain around pivot tables. I never have been able to.
I'll admit, I've been using R for over 10 years, and I was the example for this workshop. I want to show you how to make an untidy data set tidy. I want to show you how to do it in Excel, and I'm going to show you how to do it in R. And in my head, I was like, okay, pivot table. I kind of conceptually know what that does. And when I was trying to do this in Excel, I was going to the pivot table macro or whatever it is, and I could not make heads or tails of it. And I've been doing data science for over 10 years. So whatever. Point is, think about tidy data. When you do have the need to make data wide versus long and summarizing it, I think the tools available in R that are built off of these core principles of tidy data are a lot more simple and intuitive than trying to sort of use the pre-existing tools available in Excel, which was admittedly probably someone's conception of what was easy at the time. So, all right. So let me just show you an example, and this is kind of a watch and learn. I have two approaches here, again, because I don't want this to be an R workshop, but I'll show you what I mean by untidy. And this is kind of a fake data set that I put together. It's in Excel, and this is like, I picked this example because I oftentimes receive data that looks like this. There might often be like colors associated with this, and I'm like emailing the person like, what do these colors mean? But data is organized this way because it looks nice. You might see a table that looks like this in a paper, but this is a horrible example if you want to actually analyze this data, say like joining it with other data sets or just summarizing it in some way. So this is a good place to start. This is untidy because not a single row is an observation. There's columns that are spread out. There's more than one value in a cell. So this breaks all sorts of rules. So bear with me. I'm going to try to do this on the fly, trying to make this a tidy data set. So I will, first of all, I think, let me just zoom that in so you guys can see that a little more easier. All right. So I'm going to delete this. Oh, what is this data set, first of all? I had an idea in my head. This is 3 different bays. I'm sure these are real bays. Thunder Bay is a real place. But these are like habitat coverages over time, looking at in acres. And I think I had like a categorical value that was meant to be some like qualitative description of the coverage. I think it was just random. But again, you might receive a data set that looks like this. So we're going to make it tidy. So I'm going to get rid of this. I'm going to make sure there's an actual value in each cell. And so here we have like date spread across multiple columns. So that's like a terrible no-no for tidy data. The date itself should be a column. So I'm gonna make a date column. So I'm gonna insert, I'm gonna say date. And so here I'm just gonna do a lot of copying and pasting. 2019. Scroll that down. And so now what I have to do is like copy and paste these into their appropriate place. I know this is painful to watch, but this is painful on purpose because I'm going to show you how to do this very easily in R if you aren't already using R as a platform to do this. So there's 2020. 2021. Okay, and then I got to copy these guys down here. I already did that, so I can actually get rid of this. All right, so this was what, acres category, something like that. And then I just got to copy this 3 times because this is just a repeat. Okay, so this is close to tidy. We have pretty much 1 observation per row, 1 column, but we still have multiple values in a cell. So then we just have to separate these out. And then I think that's, where is that? See, now I'm like showing you how little I use Excel to do this. Oh, I know what it is. It's text to columns. That's what I'm looking for. All right. So delimited by a space or a dash rather. Okay, there we go. So this is tidy. Actually, I'm gonna remove all the formatting. Now it's really tidy. Oops. Whoa. So clear formats. Okay. So now it's tidy. Okay. Now we follow the 3 rules. One column per variable, 1 observation per row, and then no doubled up values in a cell. And this is also rectangular and flat. So like, you know, there's no dangling cells. There's no weird formulas in each cell. I actually did that by removing the formatting. So easy peasy. So you can imagine if you have any data set larger than this, it's going to be close to impossible to try to do this. And so now I want to show you briefly how to do this in R as motivation to learn R if you're not already using R. So I'm going to open up a new script. I'm going to use the tidyverse. So I'm just going to load that in. Actually, zoom in so you guys can see what I'm doing. Okay. I'm going to load this read Excel package. This actually lets you import Excel files into R. So I'm going to say, I've actually got it on my desktop. So I'm going to import it, desktop. Untidy, there we are. Okay, so I've imported it, and see what actually happens when we import this. It kind of tries to like figure out what's there. So remember, this was something that was spread out across multiple column headers. So this is already kind of a problem. So you kind of got to force it to make a format that makes sense when you actually start wrangling this. Actually, it's a trick. So I'm going to skip the first row. So now actually we're a little bit better now. So now we just got rid of that. So we know that this is now location, this is habitat, whatever. So in the interest of time, I'm just going to copy and paste all this. So here's the answer, right? But I'll explain what this does. Okay, so I'm using a couple of functions from the tidy package, which is part of the tidyverse, actually. Yeah, I'll leave that there. So tidyr is basically a set of tools that can manipulate the data in a way to make it tidy. There's several other packages in the tidyverse that can help you do this. dplyr is another one. But essentially, I'm reading in the file, skipping the first line. I am filling rows that are blank. So let me just, oops. Oh yeah, I've got to change the path here. So if I just write in the data there, right? So this is still the untidy format. I'm going to fill in these empty values using this fill function. So I just did that for the location column, done. Now I'm going to pivot it. So this is kind of where it's dangerously close in concept to pivot tables in Excel, but now we're just kind of making these final 3 columns that are in wide format into long format. So we're just sort of pivoting them from columns to rows, again, to make one row an observation to follow the tidy principles. And so we're saying these are the columns we're going to put into long format. We're saying that these headers are going to fall into the year column, and these values are going to fall into the acres and category column. And these are just names that we're assigning it. So we do that. So now we have it in this long format. Again, this is the name we said the years are going to go in. This is the name the acres and category are going to go in. And we're almost there. And the last step is just to separate this column into 2, because again, we can't have more than one observation in a cell, or in this case, an element in that column. So we use the separate function, which splits those out based on the limiter, splits them out into these 2 new columns we're calling acres and category, and it's doing it by this separator. So then we're done. So that's how you do that in R. It might not be obvious why this is an improvement by doing it by hand in Excel, but like I said, if you have any file that's like larger than the example we have here, it's going to be a lot longer, a lot more challenging. And we also have a record of what we did. That's like a critically important like step in open science, is like we have this script here that is a literal set of instructions that is, if we wanted to do this over and over, we could. It's repeatable, it's reproducible. So going through this by hand in Excel is just like, oh, let me just do this by hand. And I don't know if I wanted to do this a week from now, what the heck I did. Like, you saw me struggling through this. You know, when I made this module, I did this when I was preparing this exercise, but I couldn't remember what the heck I did when I'm going through it on the fly. So kind of made my point for me, sort of. So yeah, that's kind of the basic principle for tidy data. I don't know if you guys want to take a second to try to do this on your own, download this file and try to do it by hand using your platform of choice. We can certainly do that, or we can take like a 2-minute break if you guys want, and you could either do this or, you know, you could take a break. But
yeah, that's a good break point.
Okay.
Yeah, play around with that. I did have one question though. If you go back to your R Studio, when you initially had it fill the location, how did you specify what locations got filled where?
so this actually follows a simple procedure of just filling things down that are empty based on the value filling NA values, so missing values are
Based on
empty,
the
basically
previous
the previous value.
Okay, that's what I wasn't sure about. So when you're tidying data like that, that have missing cells that are, you have to make sure that the previous value does in fact represent
Exactly.
everything up till you get to the next value.
Yeah, and if you look at the help file for that function, you can actually fill it from the bottom up. So there's this direction argument, say fill down, up. I don't know what down, up, or up, down does. Probably some algorithm that treats things differently, but yeah, like if you knew that the previous value was the actual missing value, that's kind of something that you have to do as a responsible data scientist. You have to look at the file you're importing and making sure that the values that you're filling are what they should be. And you know, if it's ambiguous, you need to ask the data provider what those missing values are, or better yet, there's like metadata associated with that those blanks are, you know, actual just missing because shouldn't, you know, they didn't want to be redundant.
Yeah.
Even though, you know, we know that, you know, through this last discussion, that's not a tidy way to show your data, because that missing value is actually something in the data set.
Right.
So
yeah, and what I like about this process is it forces you to articulate what it is exactly you're doing, where, as Marcus so eloquently demonstrated, and as I've talked about PTSD, there's many instances where you start moving columns and you start creating things, and your mind starts to drift, and then 5 minutes later you can't remember, wait, what did I do now? You got to go back and retrace your steps, which isn't easy to do in Excel. Here, you have to logically tidy the data in your head first and translate it into the code before anything ever happens. And then of course you've got the version control too, so you can always go back.
yeah, and actually this is my test repository. So I'm actually gonna push this up to GitHub, because now there can be like a actual trail of what I did. So I need to save this file, import my data. So just to show you again how this works, I just save this file here, and this is like a sort of cookbook of how to tidy this data set. You'll see in the Git pane here that this is now a file that is able to be tracked through Git. And so these little question marks mean that, oh, it's never seen this file before. So it doesn't know what's changed, and that's what the question mark mean. But basically now it's something that Git can track. This is the first instance of that file. And so I can stage it, meaning I'm gonna say, I wanna push this up to GitHub. I'm staging it to be pushed up there. I can do the commit. And so all this green right here is basically like, says this is all new information. Like this is a new file. If this was a changed file, it would be that sort of side-by-side look of the green being what was original and the red being what's changed. But since this is a new file, nothing's changed, it's just new. So I'm gonna say added, import, and tidy script. So commit. So now everything's like on board, everything's cool locally, but I need to push this up to GitHub. So I hit this green button and it's on GitHub. And if I go back to that repository, I should see it on there. So I think I actually made that on my own, not Tbep's. Yep, test repository. See, it says updated 15 seconds ago. Isn't that cool? And there it is. It's right there. So the file's on there.
And there's everything you just told it to do. So you can always go back and look at it, or someone else can, more importantly, can understand what it is that you do with the data.
Exactly. Now, if I ever made changes to this file, I added more routines, or there's different files I'm importing with this script, I would commit those changes, push it up to GitHub, and it would be there. And you would see those changes all in that file tree. Yep. And so there's everything we've done so far. 2 hours ago, we made the first commit. And then a minute ago, we just added that file. So, and if I ever go someone like I've been doing a lot of working from home as well as working in the office, I never like have a flash drive that I transfer between my computers. I have all my projects on GitHub, and I can just sync them up through GitHub if I'm on my work computer at home versus at the office. And this is kind of like my centralized place to keep everything. So
I'm also old enough to remember zip drives.
mm-hmm.
Anybody remember zip drives? I did my thesis on a zip drive. A bunch of them had all stuff in them.
Oh, that hurts.
It does, doesn't it? It does. Man, we've come so long. We've come so far in 20 years. It's really in the last 10, because you said you've been using R for 10 years. Right?
Mm-hmm. Yeah, I started using R, well, actually almost 14 years now, because I started using it in 2007 when I started grad school. And at that time, it was just used in universities primarily. And it was really cool to see R develop in that time.
And isn't R an offshoot of S+? Isn't that where it originally code came from?
Yeah, and a history lesson, I guess. S+ was something that was developed, say, in the 90s by Bell Labs, which was a phone company, I think. And it was something that they just developed to use internally, but it was, I forget how it became something beyond Bell Labs, but the reason that when you assign an object to something in R, you have to use the less than hyphen. That used to be a button on the computers that they had at Bell Labs that they could just press. Because right now you have to, use shift left and then hyphen. There's a shortcut you can use in RStudio to make it easier, but a lot of times people ask, why do they have to use that complicated assignment operator? And it used to be a button. So
you can find an old keyboard from a Bell Labs computer and still has that key in it.
Anyway, we diverge. So let's take a few minutes break. Let's reconvene at 50 till, or 10 till rather, 50 after. And we will continue with the discussion about data dictionaries and metadata.
All right, we'll see you guys in a little bit.
All right. Hopefully you guys got some caffeine or a little break. Any questions about any of the tidy stuff before we start talking about data dictionaries and metadata? Was that old information for you guys or new information? A little bit of a mix. I mean, I have to remind myself often to keep using tidy. So it's good review nonetheless. So we will conclude this third module with the slippery slope to metadata. So as I said before, once you can sort of mentally wrap your head around the tidy data principles, you can start thinking about ways to conceptualize pieces of information in your data and ultimately how that can sort of lead towards metadata documentation, which again will not just do yourself a favor for the future, but open up kind of this broader arena of data sharing and data repositories that can go a long way towards collaborative science in an open fashion. So with data dictionaries, I mean, the concept is really simple. It's just a way of describing what's in the data set. And I think you might be surprised if you've never used this concept before that you might uncover some mistakes or flaws in your way of thinking about how you've structured your data set. Because once you start putting like literal descriptions on your data columns, what's in there, what are acceptable values, you can sort of understand what should be in your data set. And so all it is really is just a description of what's in the data. It could be like a simple exercise of, say you have a data set or you have some concept of like, say you're going to go out in the field, for example, and you're going to start collecting data. It might be good to start with a data dictionary, because then you can start thinking about, well, I'm going to be collecting X, Y, and Z. This is the format it could go in. And so you could start on a whiteboard, or you could start in Excel and just start writing down, well, what are the column names going to be? This is your first step. So again, this is like a tidy concept in practice here. You want all your data, one variable in a column, basically. So start with your column names, and then in each column, what is the type of data that's going to go in there? So if you ever taken like a basic stats class, you know that data pretty much come in two flavors, categorical and continuous. So is your data in that column going to be categorical? Is it, if it's text information, it's probably categorical. Or if it's numeric, are these continuous values or are these integer values? What are acceptable ranges of values on these pieces of information? So, going through the types of data reinforces the concept of one type of, data in a particular column. And then when you talk about acceptable values, this goes a long way for QA, QC of the information. So if if it's a categorical variable and the acceptable values for that category, like say hot, moderate, cold, those could be the three things. If something is not those three values, then that's a data entry error. And so from a conceptual perspective, that's a pretty big QA, QC flag, but you can literally build these tests down the line that I was talking about earlier of verifying that the value of or the data in the column are of that particular value. So it's useful exercise to go through. And then finally, you could talk about a description that each column is. So this could be like, a general narrative of the stuff in the column. So very straightforward. And then I have some kind of general rules of thumb that I think are useful to think about when you talk about data dictionaries. So in terms of naming columns, this is kind of like, when I think about it from a data science perspective, you want to be as short as possible, but also have some descriptive quality to the name of a data column, because you want it to be recognizable, but not long enough. Like if it's something in a big, long analysis script, it's this long name of a column being repeated over and over, that can be a headache for like reading analysis workflow. So try to strike a balance between brevity and description. And that's sort of a good way to approach it. Column names should also be kind of, avoid spaces, avoid commas, that sort of stuff, because some software can interpret that as like the start of a new column, for example. A lot of the tools in the Tidyverse are actually pretty good at recognizing that. So it's less of an issue as it was, say, like 5-10 years ago with R, but it's still a general rule to, try not to use special characters or spaces in a column name.
Before you go on, Marcus, I'm just curious, and you guys can either, type it or just say it, but I'm just curious with the group that we have, what kind of data do you all find yourselves using or collecting mostly?
All of them?
But just in general, like, are you dealing a lot with biological data? Is it, water chemistry data? I'm just curious, what.
For me, it's like a lot of data that could be used for H&H modeling. So bathymetry data, LiDAR data, DEM data, water surface elevation, velocities, and then also like water quality, like different chemicals in the water, salinity, waves, wind speed, land use, soil type, all of those type of data.
So I know with LiDAR, having worked with LiDAR data, you end up with thousands and thousands of rows of data. But the good news with LiDAR is there's a lot of metadata and a lot of strict conventions that go along with it. Same thing with bathymetry. Of course, depending on what type of bathymetry data it is, it's side scan data or whatever. There's a lot of metadata that goes along with that.
Yeah.
Yep.
Yeah. So, this idea of a data dictionary, when you talk about data quantity, this is an exercise that is manageable if you have, say, a data set that you've collected for a particular research project, like say going out in the field and you're getting seagrass data. Something like this makes a lot of sense. If you're dealing with data that's produced through some kind of remote sensing platform, as an example, like LiDAR collection, you're not going to be the one that's making a data dictionary. That's like agency curated data.
Yeah.
But still, if you're importing LiDAR data into analysis software, you're going to be faced with say you're looking at the header of that information, the first 6 rows or whatever, you're going to see column names. You're going to see, data types in the column, and you're going to want to know what that information is. And so, at least in my mind, the first thing I do when I import a data set is I look at the first 6 rows. I do, there's like a head function in R. I think Unix, if you use Linux as an operating system, that's where it comes from. But you can look at them, and I want to know, okay, what is this column? What type of data is it? What are acceptable ranges? And how might I use it in downstream analysis? Because that's the first step in follow-up analysis is what are you working with? And so even if you're not literally creating a data dictionary, approaching a data set from that perspective of what's in the first 6 rows, what are the column names, what am I looking at, types of data, especially like the character or qualitative versus numeric values, that's the first question I'm asking. So,
and Marcus, I think because right now in the state of Texas there are 2 concurrent project named Texas Disaster Information System, or TIDIS, and Texas Integrated Flooding Framework, or TIF. And one of the main tasks that we are doing in these 2 projects are defining those data dictionaries and a uniform metadata format for all the efforts that basically involve any type of data collection. So I think because you're talking about this open science with different people, it's really good to I think one of the biggest steps towards having an open data or an open science is having a uniform and a unique data dictionary for each data set. So when people go out and then they collect the data and they want to share it with other people, they all are following the same rule and the same format So that will, reduce the confusion a lot, because, a lot of times I get some data and it's a completely different language to me because I don't understand those, even though if I look at the dictionary, because, this is like a local regional level, I don't understand it.
Yeah. Yeah, and it's challenging too, because there's a million different standards for different types of data. And if you look at the evolution of just software or information technology over time, like it's sort of this ebb and flow of like proliferation of standards and people saying there's too many standards and then trying to develop a common standard to address all the standards, but then it's just inevitably sort of evolves over time.
That is not possible, but for example, within each discipline, they could agree on one type of standard. So hydrologists could have their own standard, water quality people could have their own standard, sediment people could do the same thing.
Right. And all too, if you think about it, the data repositories that are domain specific often have accepted standards for different disciplines. Like HydroShare, I know is a popular one in hydrology world. I'm sure they follow a particular standard that might be the accepted standard for that community. And if you want to upload your data to HydroShare, you need to be following their standards. So say you're starting a new project and you're going to collect novel information, thinking about how that information is going to conform to that standard from the beginning of a project, so you can, again, save yourself the headache of trying to make it conform to something after the fact. It's going to save you a lot of people. So, yeah.
Thank you.
And I'll add to that, with estuarine data, when you're talking about, hydrology or water quality data, it becomes really problematic, and knowing the right questions to ask in the absence of a data dictionary that has all those variables accounted for, like, time of tide, what was the tide, what were the winds, these things all matter.
Exactly.
Analyze those data. I get data all the time from estuaries, and we're making management decisions based on data that I don't know if that was on an outgoing tide, incoming tide, was it a windy day, did it rain? Those are all things that are often missing from those standardized data sets like STORET, or in our case in Florida, we have something called WIN. I forget what that means. Water Information Network. Yeah. You don't feel like you win when you use it, believe me. But those are things I think and I think, if I understand you correctly, it sounds like you all are in a position where you're trying to create these data dictionaries, which is a great position to be in.
Yeah.
Yes.
You can write these things now and maybe head some of that off.
Yeah.
Yeah, the state of Texas is spending almost $100 million on this type of data, standardizing the data collection and storing data in one place, so everyone could go and have access to it and manipulate the data the way that they want.
Yeah, and that, this is a sort of a sidebar comment, but everyone, I think it's easy to understand the value of data standards and how they can lead to better data storage, access of information, all the FAIR principles, whatever. But the fact of the matter is, a lot of people are developing their own standards and their own way of doing things. And it might work for the state of Texas, but there's researchers that are looking at data at the national scale or the international scale. And how do you reconcile all these differences and different standards? And it's always going to be a problem. So I don't have the answer to this and how this can be done. But one thing that I have seen that is maybe one approach or one slant to getting at the problem is a lot of the data repositories are now falling under this sort of general concept of being a federated data repository. And this is the idea that, you have basically this problem of all these different disparate repositories using their own standards, and sort of they all realize that, we're all doing things differently. How do we kind of make sure that let's not contribute to a bigger problem by doing things differently? Let's also follow the same rules. And so that's this concept of a federated data repository, where it's like there's this sort of centralized network, but there's these nodes of the network where each node is a separate repository that where at one time it was doing its own thing, But if it wanted to be part of this bigger network, it basically said, oh, let's just tweak our standards a little bit to follow the accepted standards of this bigger group, so we can then sort of, through the collective good of everybody, make
Correct.
sure, you know, we're all buying into this.
Yeah, I think one way to look at it is like, you know, for most of the data that, you know, people are collecting, there is a lead agency, whether at like federal level or at like, you know, nationwide or like state level. So when it comes to flow data, USGS is the standard, right? So basically what we can do is like, you know, if you are interested in go and collecting some flow data, just follow the USGS metadata as the bare minimum. You can add whatever you want on top of that, but at least have those attributes in your metadata to make sure that people can use it, and it's like, you know, that is comparable with the data set that other people are collecting.
And that's a very good point. It's dangerous to try to develop these things from scratch, because like, you are going to be producing something else that then probably have to be reconciled in the future. So very good point. The federal agencies oftentimes have standards and practices that they're in a position to try to promote broader use of these things, you know, because by their very nature, they're at that level organization that they can try to do that. That's, I think, one of their roles. Is actually have some examples from USGS that I think are valuable in the open science community to sort of work towards some of those broader concepts using some accepted standards. So yeah, so all good discussion. Yeah, we actually hit on a lot of the challenges that I think are worth pointing out. So the data dictionary, again, I mean, I'll be honest with you, I've done it one time. I've developed a literal data dictionary, but I use it more as just a mental exercise when I think about organizing information. Every time I get a new data set, I always look at it, and I always try to understand what's in each column, what the values are, what are general accepted ranges. I never blindly start analyzing a data set, you know, like running t-tests or something, without like looking at the data first and make sure I know what's in it. And oftentimes that's just sort of going through the mental process of what the heck are the columns, what are the values, and just developing that mental construct. So anyway, but that's still, you know, it's useful to think about that, because you can use that information to then develop metadata. And as we're just talking about, you can do that with often federally accepted standards or state accepted standards that are following these federal guidelines. So let's just have a discussion about metadata. This is the last topic in this module. I think we all kind of know what metadata is. It's information about information, if you look at the sort of Latin root of meta and data. But there's, you know, on your path towards like open science, you can be as general with metadata as you want, or as detailed as you want. I mean, obviously, it's better to be more detailed. It's better to follow strict guidelines. But fact of the matter is, if you've never done metadata before, doing a little bit, whether it be a general description or something more involved, is better than not doing it at all. Because it's just, you know, in the name of progress, incremental progress is better than no progress. So I wouldn't be discouraged if you've never done metadata before, that you feel the need to sort of figure out what the federal standard is. Obviously try to look to that as something to move towards in the future, but you know, it might take a little while for you to get there. So just think about just generally what the purpose of metadata is and how you can sort of develop this narrative around it. Because I'll describe it as basically, you know, who, what, when, where, why, and how. If you can develop that narrative and sort of write that down for a data set, that's a lot better than not doing it at all. And then you're sort of well poised to begin, you know, taking that information and making it conform to these broader standards that might apply at the federal level.
My exposure to metadata started with GIS. And working with you know, populating the metadata in a GIS file. And there, you know, I don't know if you all are involved with, you know, communities of practice, but that's another way to sort of vet some of this, like Amin, you were saying in Texas, where there's these working group that's trying to come up with what is the best metadata, best approach to capture all these various data sources. A few years ago, through CERF and GERS, we set up a seagrass community of practice in the Gulf Coast. And a lot of discussion was had about this very question, because when you get away from some of the more mature types of data like mapping, GIS, hydrology, LIDAR, flow data, you get into the biological realm. And so, and Laura and Jonathan, I'm curious too about what kind of data you all collect, because I kind of span both worlds. I do a lot of work with water quality, with flow records and things of that nature. But then I also deal a lot with biological data, with percent coverages, with Blanc measurements, with biomass. And metadata becomes a lot less clear when you're dealing with biological data, because there is no set standard that I've been able to see. There have been many attempts, and there are examples out there, but we have this issue all the time here in Tampa Bay and along the west coast of Florida, where we've got data sets that, in some cases go back 30, 40 years, but even the data sets that are being collected today, and Bob, I know you've had direct experience in this too, where you're hired to do a job to go out and collect, let's say, submerged aquatic vegetation data. You're going to go out and set up these transections, go out and you're going to collect all this data. Well, it's great for that project, but when that project ends and a new one maybe 5 or 6 years ago starts, then you got to go back and look at that and say, well, what did they do? How did they do this? Why did they do so? All those questions: who, what, when, where, why. So I'm curious, from Jonathan, you and Laura, I mean, what kind of data do you guys deal with, and is this an issue for you all?
I'll go ahead. It definitely is an issue. We collect a lot of oyster biological data, and percent cover density is important. But then if you're dealing with density, it's probably, the data is not a density, it's a count inside of a quadrant. So how big is the quadrant? That's metadata. So there's a lot of, and then there's a lot of, like, the last data set that I worked with this, the metadata sheet was like as big as the it was almost as big as the as many columns, et cetera, as the actual data sheet itself. And of course, we also, and it's good to be here today because we had it as a separate tab in the same Excel file. And so now I'm seeing that that's not a good idea, right? We want to have tidy, only one worksheet per Excel file. But yeah, this is really helpful because that metadata tab had a lot to it.
Yeah. And I'd be willing to bet that if it was a separate tab in an Excel workbook, then it wasn't following a broader accepted community standard for what metadata could be if you're, say, going to submit that to a repository.
It would have been, that would have been a rough one to submit to a repository, no doubt.
Yeah. There's a lot to say about metadata. I'm sorry, I don't want to interrupt Laura if you had something to say.
Oh, sure. I just thought I'd add, I work with a lot of different kinds of data. So this is good to think about the various types of metadata in my data sets. So I work also with like oyster biological data in some respects. So we have we have multiple varied pieces of data sets. And part of the data problem I'm thinking about is how we store them in different ways. So we have a historical data set that goes back decades for not only for mostly like a histological survey. So we have information about disease prevalences. We have information about connected to another lab's data about mortality at the same exact sites. Some of that, over time, sometimes they collected like temperature and salinity. Sometimes we don't have that information. Sometimes the locations are similarly named. There is a long rock and there's a long shoal, and they are not the same spot. And sometimes they only know that because one of them is in one river and one of them's in another. And they're like, okay, this one was labeled wrong. So there's all of that. I also work with molecular data. So I work with presence absence data. I work with quantitative PCR data. I work with molecular sequences. And that's a real challenge, even though we have like standardized data repositories for DNA sequence data. It's very frustrating when you go on to say GenBank and you look up a particular sequence record, and there are places to put your metadata, but it's all about how well it was initially curated. If they have, say, the location included, or if they, you know, how well annotated all those pieces are. So there are a lot of metadata questions in my my research realm. So I appreciate thinking about that. And our data, I think, could be stored in a better manner. We have, sorry, my internet's a little shifty. We have a logbook that we put our metadata for cases. So we'll get like a group of samples. It'll all be considered one case number that's associated with a location, a number of samples, who we received it from. And then we have separate, like all of it is tagged by one like unique number. But that data is not stored in the same place as we store like the actual like pathological information about those oysters. So it's really making me think about how we could best do that, and what like all of those challenges. Like, do you have a suggestion for those types of situations where you have multiple different data sets associated with the same samples, for instance? Like, do you keep them in multiple like groups and then have like a, say, like a table with your metadata that you can join to each of those?
I mean, that's like the core challenge of like database management. You know, how do you organize information in a logical way, especially when it's like, you don't want to be redundant with the information, but you want to have it be tidy, so you can sort of create these queries to, you know, mash up different data sets. And I mean, there's no simple answer. And I mean, I think your experience is common to a lot of people, where there's historical data sets that are confusing and poorly documented. Like your, you know, long rock or example, I was thinking of I did grad school up in Minnesota, where there's 10,000 lakes, and you wouldn't believe how many fish lakes there are. But they have, you know, a unique identifier for each lake. So they kind of solved that problem. And I found that, you know, I've oftentimes had to go back and kind of create my own sort of convention for what is a unique observation. And that, you know, if you look at it from a statistical perspective, you have a particular question you're trying to ask of the data, and what is your single unit of analysis that you're thinking about? Like, what's your single observation in the sample that you have? And that's defined by the question. But when you talk about data sets, you know, you can maybe develop that single key, if you will, for different data sets that allow you to maybe combine things in ways that you weren't able to before. And it could be like a, you know, site by date combination, if that's like your unit of observation. But as a responsible data scientist, you have to maybe think about that as one way to sort of clean up your data if that hasn't been done for you. And that can be defined by the question you're asking of the data. And it's obviously complicated by the history of the different data sets you're working with. So I don't know if you have similar examples, Chris, but
no. The only thing I'll say is that the use of a unique identifier is critical. With water quality data that we used to collect, we always use the lat long, the latitude with a 0 in the middle, and the longitude as the locator ID, which worked really well until you got sites that were too close together. So when we started doing more, you know, grid rasterized type data collection, when we were doing nested sampling, we started getting points that were really close together. So the problem with that is the lat long didn't work. So we moved away from that, and we just started using a UID, or a unique identifier. And so at any data point that we collect must have a unique identifier generated, and part of that assignment process is filling out all that metadata. So there's a procedure that has to happen before we can go out and even collect a sample.
Yeah, I mean, the unique identifier is one way to do it, but I also, I've been in situations where I received a data set that has a unique identifier, and I'm like, I don't know what this is.
That's right. That's
and I've gotten rid of it.
The rest of the metadata so when you said, Laura, you were talking about how do I link these data, and we were talking about keys and how important a key is. So that UID should be the key that links the metadata with your real data or your actual data, so that you can answer those questions. Because that's one of the reasons I liked the lat long as the identifier, because I could always just pull the lat long apart, put it in on GIS, and I know where, at least I know where it was collected. With a unique identifier, it's just a bunch of numbers, and I don't know what it is.
Yeah.
So that is problematic.
And it's often sometimes specific to a particular question.
Exactly.
And if you don't know that context, hence metadata.
Yeah. And that's why I was really interested, Laura, in your answer, and Jonathan, because if you guys are doing research, in an academic setting, it really does depend on the grant. It depends on the research question, and getting others to follow suit is really challenging. And that's where it becomes difficult. How do you do that? How do you get like all the researchers? And I guess that's the, one of the ways is how we're doing it at CERF, which is trying to come up with these communities of practice so that we can, all the oyster scientists can get together and kind of agree on this is how we want to collect data. So it's happening, but it's a large ship. You can't, make quick course corrections.
Herding cats.
Yes, herding cats.
Yeah, so we only have about 20 minutes left. I think our session will boot us off automatically at 10 minutes after. I remember reading that, or 15 minutes after. So we do have one more module left, but it was more kind of an open discussion. So we can continue talking about metadata if that's where you guys want the conversation to go. But I think there's also a lot of good points that it might be worth just bringing up briefly in the last module. So
the last module is really more designed to be a where do we go from here. So we didn't, obviously open science is an evolving process, and we don't have a nice bow to wrap this up and be done with it and be like, all right, that's it, we're done. So what we wanted to do is really take the next 20 minutes or so, just have a discussion about some of the points. And we've covered most of what's in this module. We've talked about common hurdles. We've talked about, what it means to be an open science champion. One of the things I really like in this module, though, so my introduction to open science was a workshop that Marcus hosted. Well, it was pre-pandemic because we were all in the same room together. It was about 2019, I believe.
Yeah.
And he showed this graphic, and it's one of my favorite graphics because it does speak to something that we talked about earlier. And I think you were the one that brought it up, that, there's folks that are just like, I'm not going to learn this stuff. This is like a foreign language to me, and I don't have time. And that's a real hurdle, right? We all face the time crunch. To sit and be able to learn this stuff and understand it takes time. So that's kind of what this graphic, I love this graphic. Where did you get this? Is this from that website where all the cool graphics are?
So I got this from an open science workshop I took in 2017, which was 2 years before you were in that open science workshop that I taught.
Yep.
But I've seen various versions of this graphic at different places, different open science venues. But this is great because people are being crucified on it. And that's like a level of detail that you don't see in many of these graphics. So
I like the guys that are falling off the, even later with the bulldozer.
Well, the
They're like still
bulldozer,
falling off
like
the cliff.
removing the dead bodies that didn't quite make it to the land of sunshine and bunnies. But jokes aside, I mean, this is an experience that many people have with open science tools. Many of them don't make it to the land of sunshine and bunnies because they get discouraged. And some of those people can be saved through perseverance, but like Chris was saying, some people will never even attempt to try to climb this mountain, and that's fine. Some people you're never going to be able to convince, but it's like, you know, if you've ever taken a course on like teaching philosophies, you know, you know, you're not going to be able to reach everybody, and you got to figure out where to pick your battles. But there's, you know, I think there's how's the gradient go? It's like the people that are never adopted, people that you don't need to convince at all. But then there's the people in the middle that will need that extra push. And those are the people you need to focus your time on. Or it could even be yourself, for example, like if you're having a heck of a time getting over this hurdle. And there's, I think, you know, two things that are really important to note, and we've definitely hit on them. You know, one, it's an investment, you know, realize that it's going to be a struggle at first. The mountain will be insurmountable at times, but realize, you know, at least I've told myself over the years that through frustration comes experience. I think during the frustration, remember that I think you're learning through that frustration, because there's been so many times I've been trying to solve a problem. I'm Googling, I'm going on Stack Overflow, and I might not be finding the answer to address that particular problem, but through that process, I may have uncovered something else that I learned along the way. And so it might not feel like you're making forward progress, you are. So just stick with it is what I'll say, you know, realize that it's an investment, and through frustration comes experience. But I think the more important part is you got to realize that there's an entire community of resources out there that are available at your disposal to help you learn these new tools, and that you don't need to go it alone. You can develop these communities of practice, I think, that are valuable resources to help you on your journey. And I got to give a shout out to Allison Horst. She works a lot. She's actually she's a stats professor at UC Santa Barbara. She's great graphics. She developed this one here. She's got hundreds of these that are meant to kind of demystify or make the process of learning these cold, inhospitable open science tools, make them more personable, and realize that kind of everybody has these shared experiences. And then I think that through these just collective effort of working together and making them much more approachable, we can, you know, learn together. So this particular graphic in particular, like, I think is great because, you know, it shows this person that, you know, achieved this task. You know, I've done it all on my own, but they've done it through the support of all this broader community of teachers and bloggers and mentors and friends and developers. And like, this speaks to me because I wouldn't be where I'm at in my career without just this broader R community that's out there that is incredibly welcoming, incredibly supportive, that I can just Google and pretty much find the answer like 99% of the time. So hopefully those are words of encouragement. I don't know if you have a similar experience with that, Chris. But
yeah, I know I do. I think the challenge though now is there's so many resources out there. It's hard sometimes. I find that I get lost sometimes in all of the resources. If you go online and you start looking at even with some of the work groups that they have for different R packages. And this is actually something that I've heard from a colleague of mine locally who is a SAS, you know, holding on by the skin of his teeth. SAS is the way to go. Doesn't trust R, will never trust R. One of the things that he always points out is, well, how do you know what you're getting is accurate? It works. How do you know? I know SAS works because I've used it my whole life. It's proprietary. You know, I hold it close to my chest. you're going out on the internets and you're getting all these packages. How do you know if it's right or not? And that, I mean, that's a valid concern. And I can see people who are new to this getting lost in all the resources. So it's almost like there's too many people in the balloons on that graphic, where I'm not sure which one to listen to first.
Yeah. There's a lot to unpack with that.
Can I add something really quick here?
Yeah, absolutely.
So you know, I'm just telling you a story that happened to me. I was guiding a PhD student when I was a postdoc, and basically he was like the best programmer I've ever seen in my entire life, and we were working on a very sophisticated model. And then he came to my office a day and said, "Oh, I did it. The model ran perfect." And we were trying to model salinity after Hurricane Harvey, which is very hard to do, to see like how salinity changed in the Gulf of Mexico. And then he showed me the results, and then I found some negative value in salinity right away. And he was not even aware of that because he was not by training any like environmental engineer or anything like that. And the opposite is also true. I'm like environmental engineer. So when I when I have a course about machine learning, I feel that, oh, I know everything. So, the thing that you just said is like valid. When we have like our course, or when we have like machine learning course, then we feel that we don't need anyone else. We can just, do it by ourselves. So here, I really want to emphasize the importance of collaboration. If you're working on like a big project that involves a lot of like data science and a lot of like, computer sciences, you need to have like a data scientist in your team. You need to have a computer scientist in your team, and vice versa. If you're just a bunch of data scientists that you're working on like a biology project, you need to have a biologist in your team. Otherwise, without this collaboration, none of the individual can like be the best in both worlds. That's not possible. That's like really not possible. So most of us as engineers and scientists, we feel that, oh, we don't need anyone else in our team. I got it. So the fact that you say how we can be sure that the results are correct is like, okay, if you're an expert in that area, like could explain the physical phenomenon, great. Have someone who can explain the numerical part for you or the data part for you, and then you explain the physical part, and vice versa.
Yeah, it's the emphasis on developing a diverse team is super critical, because I've seen this happen with students. I think it's very probably similar to your example. I mean, is they feel like they need to be masters of everything, but as a result, they end up spreading themselves thin across all of the things that they're trying to master, and all it's. Everyone wants to be an expert in everything, but it's just impossible. And especially with that's particularly true with open science. I mean, there's so many facets of it that, we're teaching a course on open science, but I'm not an expert in all of the aspects of open science. I can talk about tidy data only because I've been working with data for such a long time. But metadata is something that I'm trying to become better at. And as a result, I'm looking to other resources to help me along the way. And it's really important to sort of think about who are the collaborators in your toolbox that you can reach in, or that outside of your toolbox so you can reach out to and make them part of your own toolbox. And as we can only be experts. We only have a limited amount of time in the day. So,
and I think since we're talking about hurdles, Marcus, you could probably relate to this because I've heard it multiple times since, like, Marcus is the resident expert now in Tampa Bay on these things that we talked about. So there's a tendency now to say, oh, well, let's see, I wonder if Marcus can do this, or maybe Marcus can work this up. And so I think a hurdle is that as you mature in your understanding of open science and all the tools we talked about, then you have a situation where you become the go-to, where it's like, why do I have to learn it when I have Marcus here? Well, that's what everybody is saying. And we just, said you can't be all things to all people. So there has to be and this is where my personal interest is in open sciences. We have to continue to beat the drum that this is an investment in all our careers, not just well, let's just give it to Marcus. He knows how to do this, because that's what you see a lot in anything. I mean, and you know, we all have our niche where we're good at something, and somebody more often than not is going to say, well, you know, Amin can do that, or Jonathan can do that. Bob knows how to do that. Just give it to him, because, you know, we have all this free time and we just sit here and just wait for people to give us things to do. So it's a hurdle, I think, but it's one that we need to go back to the fundamental concepts of what open science is. It's not, I'm going to learn R and then I'm going to do it all.
Yeah.
Because now you're right back where you were before, except now instead of using Excel, you're using R.
Well,
Which is a little bit better.
I would encourage you to learn R.
Yes.
Try to learn how to do it all, because it's incredibly valuable.
It is. It is.
But yeah, that's one of the reasons we wanted to start with collaboration as, you know, the fundamental tool, because, you know, you're not going to learn everything, but if you know how to work better, work together better, you can make use of everybody's tools or skill sets and collaborative platforms. So
I wanted to touch on this one here, fear of exposure, because you know, we talked about this a little bit earlier. Do you all feel that this is a pretty big hurdle in your experience?
You mean fear of exposure?
Yeah, not for you personally, but just in the environment that, you know, each of us works in. Is this an issue? So for me, because I work collaboratively every day, I don't feel this is as much of a hurdle, because I work for a public agency. Everything we do is in the sunshine. I can't help but be exposed because of where I work. So the culture here is one of openness. It has to be. But that's not the case everywhere. When I was at LSU, that was certainly not the case. I was just curious if you saw this as an impediment or as a hurdle.
This is Bob. I know about a year and a half ago at the Ecological Society of America meeting, the issue came up, and it came out that in certain parts of the world, people had proprietary data sets because that's how they made their living. They somehow found funding to collect the data, and that's what their careers were based on. So I don't think it's fear of exposure, but it's somewhat related, and that essentially the rules that we're playing by don't necessarily apply globally.
yeah, those are the one of two big issues I think people have with open science is the data are valuable, and so there's fear of exposing the data to others that can scoop it. But there's just the other one being fear of exposure, where it's sort of your mistakes are out in the open, essentially. But I think the first one is the bigger issue here, because especially in academia, you know, there's competition for limited resources, and if you are open with valuable data sets, people see that as losing a competitive edge, because the valuable data set that lets you get the funding is open to anyone. So why should a funding agency give you resources if everybody has that data set? And I think that's a very real concern that I don't have an answer to, frankly, how to address that, especially when people's livelihoods are at stake. You know, if it prevents them from doing more research, and, you know, the future of their lab is at stake, and their job, for the most part, is at stake. We can't dismiss that concern. So I said I don't have an answer to it, but I do have suggestions of how I think people might reorient their thinking to maybe address some of those concerns. One being open all the time. You don't have to be open all the time. Right. So, you know, that's something I like to impress upon people, is that there's certainly times you probably could be closed and should be closed if it, you know, say affects your
ability to compete for funds. That doesn't mean that, say, after the fact, say you've got the funds to do this great research based on something that you needed to keep closed for a while, you can't produce a product after the fact that is completely open. Say you develop an awesome dashboard from this project that was funded by something that you had to be closed to get the funding, you could still produce open products after the fact. There's a time and place for everything, and that applies to open science too. The second thing I'll say is that just keeping a mentality of closedness stifles creativity. And if you're more open, you're more likely to meet new collaborators. And in doing so, you are maybe developing more of a competitive edge by just developing a broader network of people who you're willing to work with. So just generally speaking, I think from a personal level, I've had this happen where I've just been able to work with more people from just making my work out there and putting it out there. And they've seen stuff that I've done through my GitHub account, and they've contacted me, and I've been able to get money that way, honestly. And so there's just a different way to look at it. And that's just been, that's how I try to approach it. So
I'm curious, do you all think that the next generation that's in grad school now has a different view of this concept than the previous generations? I know, like, from Marcus's point, I've had professors, I've had teachers that they build a career on data sets, and they're already thinking ahead to their next paper. So, you're collecting data that is going to be used in future research in order to basically build a dynasty of papers. It seems like the current generation of students who will be the future scientists and engineers have a different view of that. I think they're not as fixated on publish or perish, that it's more being open, because that's how they grew up in a social media world. So everything is out there. I don't know. Do you all agree, or you think not?
I think, Chris, you and I and Marcus may be biased by kind of being in the applied data world, because in our world, data get older much quicker than they used to. Now that we have huge streams of real-time data flowing in, a 2-year-old data set is, it's valuable for your long-term trends, but it's not perceived as nearly as valuable for your immediate project. But I would guess maybe in the more theoretical world, people still protect their data, but I'm just not playing in that world. I don't know anymore.
I think, even in the applied data collections, let's say, some faculties are interested in collecting some specific carcinogenic materials like PFAS or like PCB dioxin stuff. And then those data says each sample is probably going to worth a couple of $1,000s. And then over the years, let's say 10 years, 20 years, they collected a lot of samples by writing different proposals. And what they don't want to do is sharing that data, because that's the butter and bread for their next proposal and for like their next paper, right? They have to make them public, because part of the grant, say if it's an NSF grant, for example, it says, oh, you have to make it public, but they will bury that data really hard so no one can have access to that, basically, which I really don't think is a good thing or bad thing. I'm not judging them, but I understand why they are doing it. That's all I can understand.
Yeah. There's one last thing I wanted to say. It's 6:45, so it's been a good 4 hours, so I don't want to keep you guys too long. But the publish or perish mentality is, Chris mentioned, is still alive and well, and it's an old school way of approaching traditional metrics of success. But one thing the open science community is working towards, and I think even beyond this open science community, is how do you incentivize alternative metrics of success, especially in academia where it could be so cutthroat. And there's been sort of, I think, a movement towards other ways to identify non-conventional scientific products that previously have not been noticed. And that sort of shift in what's important comes at an upper level, at the college level, university level. So it's hard to make those changes. But an example is citations for data sets are now more and more common as a metric of success, where historically they haven't been. And that's being recognized as legit citations if you look at how many citations somebody has, and previously that was not recognized. So I think there's a shift in mentality, and I think that's coming forth more in younger students coming out of academia now. And so I don't think it'll ever, the landscape will change, and it's moving towards different ways to evaluate and congratulate success. But, we'll see how it turns out.
Well, I know we're at the end. There was one last thing I wanted to just highlight, which is the last section of this module. We've kind of hit on this throughout the last 4 hours, but I do want to leave everybody with this heading that something is better than nothing. So, it's as we all go forth now and promote open science, small bites and baby steps are better than nothing. I agree with Marcus. Let's all be experts in R. I know I'm not going to go home tonight and read my R first data science, but it's always there next to me somewhere. So I'm trying to learn. And so really that's kind of the last thing that I wanted to convey is any progress is good progress. So let's keep moving towards an environment of open science and make it happen. And I think we'll get there eventually. Maybe not us, but those that come after us will.
You're more of an optimist.
Maybe I am.
Any closing thoughts or ideas from you all?
Thank you very much. This was a very great conversation. And I'm going to borrow some of those language. I will definitely cite you all, but I will borrow some of this language from the things that you shared with us.
Absolutely. Like I said,
you.
you're going to reuse any of this, and I appreciate you guys sticking in today, and we're glad it was worthwhile.
Yeah.
Can I ask one question before we take off?
Yeah.
So not really something we talked about, but do you see open science and GitHub as being useful for increasing replication in science? So either a data set is publicly available and so multiple scientists can try different analyses and see if they're replicating each other's results and coming to the same conclusion, or just by having your script and your methods detailed available, somebody else can have their own data set in a similar arena and can use your methods and see if what they're producing in Maine is similar to what's happening in Florida, something like that. Is there a replication future here?
Oh yeah. Yeah, no, I've been using GitHub almost as long as I've been using R, and that's one of the main reasons I use it is for reproducibility. Anybody can use what I've created and vice versa. And any platform that essentially limits the need to transcribe things by hand, and that's kind of what analysis code is meant to do, is eliminate that. And it's actually like a literal cookbook of a method that is going to help a long way towards reproducibility. A lot of what I do with GitHub is papers I've published, I'll have a supplementary R package that goes along with it. And so if you talk about reproducibility from an analysis perspective, somebody's reading the paper, they want to, oh, this is great, I want to apply this method. Oh, here's this R package that I can download. It's all right there. And so they could do it exactly the same way it was done in the paper. You try to do that by hand from like reading a paper that doesn't have something like that, you're not going to get the same answer. And there's a lot to say about the steps to, what is a reproducible R workflow, but that's 1,000 times better than, just the old school way of, we sampled on this day and did this, and that sort of.
Well, that's also really important because with technology, statistical analyses are becoming more and more exotic, and some of it is really good and profound. Some of it is, basically wizardry, and having that information out there for everyone to see and repeat and reuse is really critical, because all too often I see reports that are produced with all these graphs in the back of the report,
and then conclusions made based on all these plots that were done on SAS or whatever. And that you're taking a lot on faith. And I think today, because our computing power is such, we can look at data in ways we never did before. So it's really important to be able to repeat that, even with the same data set. And this is one way to ensure that we can do that.
Yeah, the last thing I'll say about that is just because a script is on GitHub doesn't mean it's reproducible. There's a lot to say about the particular software environment that was used to create that script, or at least the results from that script. And there are ways around that too. And we haven't covered that at all, but software versions, operating systems, all that stuff, that could be in metadata, but there's actually there's software platforms that can sort of create an image, if you will. Like if you've heard of Docker is kind of like the new thing that people are using to create like a containerized environment for reproducing an analysis. And it's like, that's like the standard now that people use from a reproducibility perspective. And that is something that I think is like on the cusp of where we can go as a community for reproducibility.
I thought that was a pair of hands.
They are. It's been a long day, Chris.
Sorry. Yeah, but and R itself too, there's always updates to
Oh, yeah.
It seems like every time I open RStudio, it's out of date. So
That's
and
true.
I don't know if that affects it at all, but like if you created code 10 years ago, will it still run on the current RStudio platform?
Well, yes, well, yeah. R, I think, is a lot better at that than other software, but still, it does have this issue of constantly being developed. And that's kind of the situation that creating images through a container tries to solve. And there's a time and a place for those types of applications, but start small is the name of the game, you know, and you can sort of learn these tools as you go. And by the way, also, I always try to, at the end of these workshops, say, you know, I always try to put myself out there as a resource for, you know, if you get stuck in questions. I don't know if our contact info, or is our email?
I think our contact information is in there.
Yeah.
Hey, Marcus and Chris, I just want to warn you all that this meeting will automatically close out in 2 minutes. So just heads up. Just wanted to give you all that time.
Awesome. Okay. I anticipated that. Thanks, Allie.
Yeah, and Allie, thank you too for this platform. I think, you know, hopefully you all got a lot out of it. I know it was, it's always challenging in a virtual environment, but you know, I appreciate everything that CERF's done to make this happen.
Yes, absolutely.
Well, we're happy to be able to help and support you all.
Thank you all. Bye.
All right.
All right, with that, y'all have a good night. Thank you and enjoy the rest of the
All right.
conference.
Good luck, you guys.
Bye.
Bye.